We have a lot on the docket for today, and I'm sure we'll get into depth when it comes to the problems at the foundations of quantum mechanics. But I think to begin, there are two topics that we wanted to touch on in a more pedagogical fashion. One is screening off and conditional probabilities, and the other is just what is this problem at the foundations of quantum mechanics that will be in the background or at the focus of this entire conversation. And I think it makes most sense to begin with the latter. And Jacob, since we're going to be talking a lot about the indivisibility approach that you've been working on to quantum mechanics, I thought it would be best to start with just what it is the problem we're getting at is in the first place.
Thank you, Robinson and Tim. It's really delightful to talk with both of you. So let me summarize this as briefly as I can. Quantum theory develops roughly from 1900 and on. In the first couple of decades, you have a collection of heuristic tools. They make predictions. Things don't quite fit together into a unified framework. In retrospect, we call this period the time of the old quantum theory. This is the time of Max Planck and Albert Einstein and Bohr and all these folks working on the theory. And then 1925 sees a very important development. Werner Heisenberg, quite young in his 20s, goes off to Heligoland to reformulate quantum mechanics and to make sense of the theory. And he comes back with what one of his supervisors, Max Born, called matrix mechanics. And, this was the first more or less comprehensive picture of what quantum mechanics could look like as a theory. It was very abstract. And Heisenberg made a very deliberate move that he described at the beginning of that 1925 paper, that spring 1925 paper. He said that physicists should phrase quantum mechanics, this developing theory, in terms of things that could be observed, to get rid of all of the weird, unobservable trajectories and electron orbits and so forth, and phrase the theory directly in terms of ingredients that could, in principle, be observed. Now, this is obviously a very simplified version of what he said in the paper. We can get into more depth about what he did. He independently discovered the mathematics of matrices, which had been laid down 75 years earlier by James Joseph Sylvester. He hadn't been trained in that. So he sort of reverse engineered both rediscovering the mathematics of matrices and much of what we would now call modern quantum mechanics in what we would call the energy eigenbasis, in what we would call the Heisenberg picture, rather appropriately, even though a lot of that terminology didn't exist. There was some difficulty with uptake of the theory. Many physicists were not very comfortable working with, the matrices that Born, Heisenberg, and Jordan were working with were infinite by infinite matrices. And in 1926, Schrödinger published papers in which he introduced his famous wave function as part of what he originally called an undulatory theory of mechanics. And this wave function allowed Schrödinger to write down, in some ways, a stronger, more intricate theory. The theory that Heisenberg had presented did not have a well-defined dynamical law that described in how and when and in what way atomic systems would transition. Heisenberg's theory was very good at predicting how much energy would be emitted when atomic systems transitioned. This energy could then be seen, through emitted radiation from atoms as they transitioned. But Heisenberg's theory didn't have a detailed dynamical law that would allow you to talk about when and, in retrospect, with what probability systems would make transitions. Schrödinger made a number of important contributions in 1926. He was able to replicate the predictions of energy levels that had been found in Heisenberg's matrix mechanics. But more than that, he was able to provide something like a dynamical law, something evolving in time in it's like a lawful way. And this law that Schrodinger was able to write down was a law describing how his wave function changed with time. This equation is now called the Schrodinger equation. Now, I need to say a couple of things right at the beginning about wave functions. I know that some people in the audience will likely know this, but not everybody will. It's important to note that although a lot of analogies were made between Schrodinger's wave function and the kinds of waves that physicists were familiar with from before, there are some very important qualitative and conceptual differences between the kinds of waves physicists had worked with before and Schrodinger's wave function. Schrodinger realized immediately, this is written in his original papers, that his wave function did not assign values or magnitudes to points in what we would call physical three-dimensional space. This is in contrast to like an electric field. An electric field assigns magnitudes or little arrows or directions, however you want to think about it, to points in physical space. When you have a wave of the electromagnetic field, we think of that as undulations in those magnitudes that propagate through physical space. Schrodinger knew immediately that the wave function he introduced assigned magnitudes or values to points in what we would call configuration space. Somewhat more familiarly, this would be called like possibility space. In physicists speak, sometimes we call this Q space because the letter Q is often used to denote individual possible configurations of a system. So the wave function assigns magnitudes to the different possible configurations a system can have. And if this is a system, say, of 7 particles, each of which has 3 spatial coordinates, that's 3 times 7 or 21 dimensions. That's the kind of space whose points the wave function assigns values to. And Schrodinger was quite puzzled about this. He talks about it in the paper, but nonetheless, he has a dynamical equation for this wave function. In 1926, later in 1926, Max Born proposes what's now called the Born rule, which assigns a very particular interpretation, a practical operational interpretation to the wave function. The wave function assigns a certain kind of number called a complex number to each point in this possibility space. And if you do a certain kind of operation on it, it's called the mod square operation, then you get a non-negative real number. And Max Born argued that this non-negative real number should be interpreted as the probability that a measurement would find the system in question in that particular configuration, somewhat more precisely the probability density that it would be found in this particular configuration. So what Schrodinger's equation does, it does a couple of things. One is it lets you indirectly predict energy levels of systems, but it also provides this time-evolving wave function, a law for this time-evolving wave function that assigns magnitudes to points in configuration space, which then, according to the Born rule, tell you the probabilities with which measurements will yield certain results. The measurement that will reveal the system on the measurement will produce that particular configuration. And Schrodinger, again, was very confused about this. Obviously, this discussion was had among many of the theoretical physicists at the time. Heisenberg did not initially like the idea of the wave function. It was one of the few things that he and Einstein agreed on. There's a number of letters. We have a lot of correspondence from Einstein from 1926, 1927 to colleagues like Lorentz and Ehrenfest and famously Max Born, right? This famous letter, December 4th, 1926 to Max Born, where Einstein talks about how he doesn't think that God plays dice with the universe, but then his next statement is he doesn't like these wave functions that live in high-dimensional configuration space. What does that even mean? Einstein said it didn't feel like something that could be a piece of reality. By about 2 years later, 1928, Schrodinger gives several lectures on what's now called wave mechanics. And in the 4th lecture in wave mechanics, section 15, Schrodinger describes his early views on what he thought the wave function could be. Maybe it was a piece of ontology, meaning something that physically existed. He even describes a kind of proto many worlds or Everett kind of picture where maybe to the extent that the mechanical picture could be used at all, the old mechanical picture of particles, somehow the wave function was describing the mechanical system doing everything that it could do, but in some way, some ways it was behaving stronger than in others. That's the language he used. But then he says that he no longer held that view, at least as of that lecture, that the work of people like Max Born to interpret the wave function in this probabilistic or statistical sense had eventually led Schrödinger to doubt that the wave function itself was a piece of physical reality. But the wave function at this point, I think, was cemented into our picture of how quantum theory works. When you take a course in quantum mechanics, an undergraduate course, let's say, often the course will very early on introduce the wave function. If you pick up a book on the interpretation or the philosophy of quantum mechanics, frequently the starring player, the protagonist of the story, is the wave function. And the question is, what are we to make of the wave function? The theory is built out of wave functions, and our goal is to try to make sense of wave functions. Now, I'm going to fast forward very quickly to the key problem here. 1930, Paul Dirac sews together Heisenberg and Schrödinger's pictures of quantum theory into one picture based on what are called Hilbert spaces, an even more abstract kind of space that involves the complex numbers. Schrödinger's picture could be seen as his wave functions could be, from this picture, understood as components of what are called state vectors in a particular orthonormal basis called the position basis. And meanwhile, Heisenberg's matrices could be understood as representations of the things that correspond to observables as represented as their operators in the Dirac-Hilbert space picture, but represented as matrices in what's called the energy eigenbasis, a different orthonormal basis. John von Neumann publishes Mathematical Foundations of Quantum Mechanics in 1932, further formalizing the theory. And when we teach quantum mechanics to undergraduate students now, we often present the students a sort of axiomatic formulation that some people will call the Dirac from Paul Dirac, von Neumann from John von Neumann, the Dirac-von Neumann axioms. And these axioms, they define textbook or orthodox quantum mechanics in terms of the idea that there are quantum states which generalize the wave function. These quantum states belong to these abstract spaces called Hilbert spaces that can have any dimension, not three dimensions like ordinary space involves the complex numbers. And also an evolution law that generalizes Schrödinger's law, a law that describes how the quantum state that again generalizes the wave function, how the quantum state is supposed to evolve with time. This is known as unitary time evolution, and in many simple circumstances, it can be turned into a differential equation that tells you moment by moment how the thing evolves. And this sort of evolution law is supposed to be the evolution law for a system that is not, for the unitary cases, the system is completely undisturbed. This can be generalized a little bit to systems that are open to their environments, but we get what are called quantum channels in that case. But this evolution law it does not involve things like probabilities in it. And depending on exactly the circumstances, it's more or less a deterministic kind of law for the behavior of the quantum state. Crucially, it also doesn't do things like single out measurement outcomes. That's not part of that language. So those axioms I call the Hilbert space side of textbook quantum theory. And they're beautiful and pristine and mathematical. And then there's the measurement side, the measurement axioms. The measurement axioms connect this pristine, beautiful mathematical formalism to the results of empirical investigation. The empirical axioms say that if every system is associated with a collection of abstract operators, these were generalizations of the matrices that Heisenberg introduced. These represent observable features of the system like energy or position or momentum or angular momentum or whatever. Interestingly, not time. I know that's a very important point. Time was not among one of those observables, but many of the other observables are in that list. If an external observer comes along and does some kind of measurement to, learn something, to measurement on one of these observables, then according to the axioms, the result is going to be one of these special numbers associated with the operator. These numbers are these invariant kind of numbers associated with operators. They're called eigenvalues. It's a word that was introduced by David Hilbert. And And then the question of, okay, so which one will you get? Well, you don't know which one you're going to get in general. The one that the eigenvalue, the numerical result obtained in the measurement that's revealed is given by the Born rule, a generalization of Born's original rule that provides a probability. It takes the quantum state, it takes the operator representing the observable, it puts them together in this particular way, and it yields a particular probability with which a measurement will yield that result. And then, very controversially, as soon as the measurement is done, the result is locked in through what's called a collapse or a Luder's projection. The quantum state suddenly changes so that if the same measurement of the same observable is done shortly thereafter, with very, very high probability, the same measurement result will be obtained. And though these have become the Dirac-Feynman axioms, there are a couple more things to say about this. One very important question is a question of Mariology. Now, Robert and I talked about this last time we spoke, this question about how we think about parts of systems, subsystems, and their composite systems. And the Dirac-Feynman axioms do say a little bit about this. They say that, if you have a Hilbert space of a system made of smaller systems, the Hilbert spaces are supposed to be composed in what's called the tensor product way, and there's a rule called the partial trace for going down the Mariological hierarchy. There's some Mariological structure, but not a lot. And this is one topic I hope we'll get to. So what's the problem here? Well, one immediate problem is that we have two distinct kinds of time evolution. On the one hand, we have the Hilbert space-time evolution, which does not talk about probabilities. It doesn't do things like single out measurement outcomes. It doesn't seem to know very much about external observers or measurements at all. And on the other hand, we have this categorically distinct kind of time evolution that's supposed to take place when an external observer, which the theory doesn't define, does a measurement which the theory doesn't define. And this other kind of time evolution produces a specific result. One result is singled out, and with a probability associated with it, a measurement probability. And this is just a completely different kind of evolution. And people have talked over a long time about, well, maybe there's some way to sort of get the measurement axiom evolution out of the Hilbert space evolution. Maybe decoherence is part of the story, but decoherence, none of these things, there's no deductive argument that takes you from things that don't have probabilities at all, or singling out outcomes to ones that do. So something appears to be broken here. And this gap between these two forms of time evolution, what von Neumann called, he actually reversed it. He called the measurement evolution, the collapse evolution with probabilities, he called it type 1 evolution. And he called type 2 evolution the evolution where things are evolving when they're not being measured. And the fact that there's this difference between they're categorically different and the theory doesn't define in which cases you use one or the other, you're just supposed to know. Like Potter Stewart, the Supreme Court justice, said, you're just like, an obscenity is you know it when you see it. You're supposed to just know when a measurement's been done. This ambiguity, which is just an obvious ambiguity in the axioms, that's the measurement problem. I would add a few more problems that I see with the axioms, and everybody has their own list that I think need to be dealt with. Another problem is that the only probabilities that come out of the theory, according to the Dirac-Feynman axioms, are measurement probabilities. Sometimes people will say that classical physics emerges at the level of averages from textbook quantum theory, but the averages that one uses, the averages that one gets out of the axioms, are averages over measurement outcomes averaged over measurement probabilities. That's a very narrow kind of phenomenon. And so if you want to ask about, well, what about everything else we think is going on in the universe? What was going on in the early universe before there were observers? Early universe cosmologists, people studying inflationary cosmology, talk about using quantum theory to talk about probabilities in the early universe, but there were no observers, there were no measurements going on. So there just appears to be a categorical gap between the narrow category of measurement phenomena in particular, measurement averages in particular, and the larger, seemingly larger category of averages or phenomena just happening everywhere. So either early universe cosmologists are not being honest when they talk about probabilities of things going on in the early universe. They should really say the only probabilities happened once our eyes looked in telescopes. Or there's some part of the story that's not complete, and I call this the category problem. And either one would have to explain why all those things happening in the early universe count as measurements in some sense, or make some other kind of argument, but some work needs to be done. I call this the category problem. It's not enough just to put little brackets around a quantity and say it's an average, and then say that therefore it's the same kind of average that we would think of classically. There's more work that needs to be done. I would add a third question, which is, what is the ontology? The ontology is what exists. What is the theory saying exists? I mean, the Dirac-Lanham axioms don't really make any sense unless there's some commitment to external observers and measuring outcomes existing. Otherwise, the theory is, I mean, that's what the measurement axioms are talking about. And without them, the theory is empirically self-undermining. There are no results. If there's no external observers, if there's no measuring devices, no measurement outcomes, then there are no results. The theory doesn't make any sense. So there seems to be at least a commitment to that. And in the old Copenhagen interpretation, this was broadened a little bit to talk about classical macroscopic systems existing. So there's some commitment to some kind of ontology. But the question is that really it? I mean, after all, we appear to be mereological composites. We're made of smaller things. And the question is, how could it be the smaller things don't exist, given that we exist? And where is the line? How do we demarcate when things exist and when they don't? I call this the mereology problem. And connected to it is this problem of what are we committing to say actually exists? I call that the ontology problem. So again, just to revisit the measurement problem, the category problem, the mereology problem, and the ontology problem. And I would broaden the mereology problem a little bit. The Dirac-Lanham axioms fail to have a really crucial ingredient that, for example, Newton's theory has. And, for example, that the Bohm's theory has, and that electromagnetism, classical electromagnetism has. And this is a clear mereological structure that's self-consistent both at the level of what exists, the ontology, and at the level of the laws, the nomology. Nomology comes from the Greek for laws. We can talk about a system, and we can talk about its pieces and what it's made out of in Newtonian mechanics, and we can apply Newton's laws of motion at various levels of the hierarchy of sub-objects, subsystems, and their composite systems. We can talk about forces in a subsystem, the forces on a composite system, and Newton's third law, the equal and opposite reaction law, implies that internal forces cancel in just such a way that we get consistent results. If you want to predict where the center of mass of a Newtonian body will go, you can make that prediction by looking at the whole body as a whole, or you can mentally think of it as several bodies stuck together, figure out where all their centers of masses go, and then average them, and you'll get the same answers. The answers are self-consistent. That's a kind of nomological, mereological consistency. The Bohmian mechanics has this property as well. At some point, maybe we can talk about that. It's very nice. But the textbook theory of quantum theory lacks this property. I can assign a dynamical law to a big composite system, but in general, there's no non-contingent general rule in the axioms for saying how subsystems are supposed to evolve at all. Instead, what one does is one helps oneself to the measurement axioms a second time. One uses the measurement axioms to say that, well, experimentalists will set up a system, they'll prepare a system, they'll collapse the system down to some quantum state. This quantum state will factor off of the whole rest of the universe. And then there are ways, given that starting assumption, to then be able to assign something like dynamical laws to the mereological subsystems. But you have to help yourself to the measurement axioms, which are, for a lot of people, the most suspicious part of the axioms. So, and if you ask a physicist, well, if I just give you a composite system, it's evolving maybe unitarily, can you just tell me what the dynamical law is for one of its parts? And in general, there just isn't a rule for this, which is kind of amazing. So I would add this to what I think is a serious problem with the mereological self-consistency of quantum mechanics. So I come at this, problem with this list of issues, and the backstory here, and I've been talking a lot, so I'll want to stop now. But the backstory here is, early on in my academic career, I learned a lot about the theory of stochastic processes. I don't know that the theory of stochastic processes is widely taught in the physics curriculum, the philosophy curriculum. I came at it through a variety of sort of tangential paths. I didn't really see very much of it in my philosophy or physics education. But it's a very elegant and very beautiful theory. And it bears some striking resemblances to quantum mechanics, not just because of probabilities, but also some mathematical resemblances. We use vectors to represent probability distributions. We use we can represent random variables, observables in some situations as something like as you could show like matrices, but importantly, time evolution, the evolution of probability distributions is carried out by these square matrices. So there's like a lot of interesting connections. And in trying to understand the precise relationship between the theory of stochastic processes and quantum mechanics, I made a little bit of a discovery. The discovery wasn't completely original. It had been noted 2 years earlier by a couple of people working in quantum information. So when I later looked at what had been done before, I saw that this had been noticed before. But there was an incredibly simple, elegant story to be told, a very, very simple mathematical story that yielded, at the end, a Hilbert space picture that looked just like quantum mechanics, but where we didn't begin with a wave function. Wave function wasn't introduced in the beginning. And in fact, introducing the wave function, or the Hilbert space picture, or quantum states, all of it, you could introduce those later on if you wished. It would make certain calculations much simpler. It would give the process a nice feature that is called the Markov feature, which we'll talk about. But if you just if you never thought to introduce those features, you'd still have a theory that worked. And for simple systems, you could use it to make predictions. It would be really nice. My concern, of course, was that, if you start with quantum mechanics and you just sort of take pieces out, you're going to get just a mess. But what was remarkable was you started with a very, very simple picture, and you got quantum mechanics, and suddenly all these things that we thought were primitive, irreducible features of quantum mechanics could be seen to be reducible, could be derivable from deeper ingredients. And that's just the beginning of the story. I'm going to pause now. Later on, I'd like to actually describe the simplest version of this construction so you can see how it works and how it leads to the sort of reducible picture for the ingredients of quantum mechanics. But I think this is a good place to stop.
Okay. Well, at the risk of having a somewhat disjoint beginning, I would definitely like to get back to the mereological, ontological, categorical, and measurement problems. I know, Tim, that you wanted to discuss screening off and conditional probabilities. So I'd like you to take off from there. But if you also wanted to make any comments on what Jacob said first, please.
Yeah. Okay. So I'm going to pile some more stuff on top of this introduction, but I'll try to be quick about it. Actually, I do want to respond is the wrong word. There's a little bit of linguistic terminological usage that Jacob was using a bit differently than I do, and I want to clear that up first. So programmatically, mathematical physics is in the business of finding mathematical gadgets that you're going to use to represent somehow physical reality. And so you've got the question, what are the mathematical gadgets? Then you've got the question, what's the physical reality you're postulating and how are they related? I like to make a distinction between what I call the wave function that's used in quantum mechanics and the possible object that it represents, which I call the quantum state. Now, Jacob used quantum state for something else. I think for a density matrix, I'm not 100% sure. Whatever it was mathematical. When I talk about the quantum state, I mean a piece of physical reality, which is the thing that this mathematical object is supposed to represent. Now, Shelley Goldstein gives you a nice trilemma about the wave function. He says either it represents nothing, or it represents something but not everything, or it represents everything in physical reality, right? I mean, those are your choices. Some people try to get away with nothing, like the quantum Bayesians who say, those wave functions, they don't represent the physical world at all. They're about our beliefs. Chris Fuchs will say, psi should be written on your forehead because it's a representation of your information or your knowledge or your beliefs or whatever. Okay, that's a view. The many worlds people say it represents everything, okay? Absolutely everything in the physical world is one way or another coded up in the wave function. Then you have the Bohmians and others who say, well, it represents something, but not everything. It represents something non-local. There's more than that. There's some local stuff. This is the way of Bohm and the way of collapse theories that introduce a local ontology. Okay. Now, let me just say first, before I wanted to get to something else, but the view that it represents nothing, which sounds like what Jacob is proposing, okay, then you can clear me out after this. But let's begin with kind of intuitive reasons to think it represents something, which is just the regular two-slit kind of phenomenon where you get these interference patterns. The way we know how to predict interference patterns is by waves, something governed by a wave equation. Water waves do it, electromagnetic waves do it. Because the Schrodinger equation, which is the standard way the wave function is supposed to evolve in time, is a wave equation, it naturally gives rise to interference effects, constructive and destructive interference, these interference bands. And so that's a reason why everybody I know thinks it represents something. Okay, there's something in the world. It's true the mathematical gadget is defined in this high dimensional space, and that's puzzling because it can't represent a field like an electromagnetic field, classical electromagnetic field, which is on physical space. So there's a puzzle there, but just the interference effects usually lead people to say, hey, something's going on here, right? Something's in contact with both slits, right? Something's interacting with both slits because the phenomena depend upon whether only one slit is open or the other slit is open or both slits are open. All right, so that's, notice, a kind of causal condition here. You're saying, look, the state of each slit is causally relevant to the effect. So there must be something that's interacting with both slits and then going on and forming this interference in kind of the usual water wavy kind of way. Okay. If, the main questions you have of any physical theory is what does it postulate and how does that behave, right? What is there and how does it behave? What's the ontology and what's the dynamics? This is a reason to believe some real part of the ontology corresponds to the wave function and that it evolves by a wave equation, like the Schrodinger equation. I think, but again, he can correct me, Jacob doesn't think that at a fundamental level that is what's going on, that maybe you can have talk in those terms, but that's not fundamental behavior. It's somehow emergent. Okay, so this is just one thing. Now, the main thing I want to talk about is this Markov process, Markov condition, because it's a very simple condition, but now we're getting into an entirely different field, which is causation, causal models, the analysis of causation. And I just want to very quickly run through this so people understand. It's a truism that correlation is not causation, right? Everybody knows you can have correlations between A and B, but there's no direct or even indirect causal relation between A and B. On the other hand, all our evidence for causation is correlations. Right? That's the evidence we have. That's what we point to in the data to argue that there's causation is correlations. So even though you can't define causation in terms of correlation, you use it to test. And just to be clear, because this is standard literature, but it's not talked about in people talking about quantum theory so much, but just standard literature. So take a correlation that exists, that for sure is there in the data, between people who have ashtrays in their houses and people who get lung cancer. Okay. So what do I mean a correlation? I mean, okay, take the percentage of people, and these are just percentages. These are just statistics. Take the percentage of people who have ashtrays in their houses that get lung cancer, the percentage of people without ashtrays in their houses who get lung cancer. They're different. And there's a positive correlation because if you got the ashtrays, you're more, higher percentage gets lung cancer. But nobody thinks that ashtrays cause cancer and nobody thinks that cancer causes ashtrays, right? So that correlation, we think, is explainable in terms of a common cause. In this case, smoking, right? Because some people smoke, they're both more likely or more of them have ashtrays around and a higher percentage get lung cancer. How do we test that? Well, one thing we do is we say, all right, let's just check whether if we condition on smoking, so we had two things to begin with, which is ashtrays and cancer. Now we're going to put in smoking as a third variable, and we're going to condition on it. We're going to say, okay, let's just take the smokers and now see how many get cancer, and whether adding the information about the ashtrays makes any further difference to the statistics. And if it doesn't, which it doesn't, or at least, the first order doesn't, then we say, smoking screens off these two variables, these variables that are correlated, the ashtrays and the cancer. Once we condition on the smoking, the dependency on the ashtrays goes away statistically. It just doesn't exist anymore. So that's called a screening off condition. It's very important when you're doing causal analysis, because screening off gives you reasonable clues about what the causal structure is. Okay? Now, the Markov condition that Jacob is very boldly suggesting we consider abandoning, which has been part of all physics up until now, and not just deterministic, but also indeterministic physics, right? You might postulate that things aren't deterministic, but still you would normally postulate the Markov condition. What does that say? Well, suppose here's a correlation we have. We know that people who get shingles in old age had chicken pox when they were young, right? And so you say, well, there's certainly a correlation there. In fact, if you never had chicken pox, you'd never get shingles. And if you had it, there's a certain percentage of people get shingles. Now, suppose we have two identical twins, and one of them gets chicken pox in their youth and the other doesn't. And then the doctors say, well, the one who got chicken pox just completely recovered. All the traces are gone. The two twins are back to being biologically and medically identical at, say, age 10. Then normally you would not expect for the shingles to show up later for the one and not the other, right? That there'd be more percentage. And why? Because you think, well, gee, if the shingle pox at age 6, if the chicken pox at age 6 was one of the causes of shingles later, that had to be transmitted through time somehow in their body, right? With some antibodies or virus or something hanging out inside the body from the early age to the late age. And so you'd say, if we could statistically condition on the entire state in between the earlier one and the later one, that should screen off in earlier information from later events. It's just the same idea that causation from the past to the future only occurs because it's carried continuously continuously between the past and the future by something physical. Something physical is carrying it on. And so that's one problem you have in the causal modeling literature is just that causal models, which tend to be just graphs, directed graphs, get very complex. The number of possible ones blow up exponentially. And so all the time, researchers are looking for constraints they can put on so they don't have to search through all of them. And those constraints often come from beliefs about what causes what because of time order and so on. But also the Markov condition is just assumed, right? You think it couldn't be that the earlier episode of chickenpox just reaches out across time from their early age to their seniorhood and induces shingles, right? It had to be by some intermediate continuous process carrying that information forward. Now, of course, if you give up on that condition, you have a whole bunch more possibilities. I mean, you're getting rid of a constraint, and whenever you get rid of a constraint, you open up things. But that's a pretty radical suggestion, right? It's what we might call temporal action at a distance. People know in quantum mechanics, there's a lot of worries about spatial spooky action at a distance, and Einstein didn't like that. And a lot of people didn't like it and wouldn't accept it and shouldn't have accepted it until Bell gave us very strong reasons to think you can't get away from it. One can imagine that maybe we want to give up this Markov condition and say earlier facts can have an influence on later facts without having any influence on the intermediate facts in time. But I would think you'd really need to be pushed into that in a very strong way, right? And even stronger than some aesthetic preferences or something like that. I mean, it's a really big deal. And so I think, as I understand it, I just believe the wave function really does represent something physical. Yes, not something local, not something that's in regular space, but it's there. And it evolves continuously through time, maybe deterministically, maybe not. I'm certainly willing to imagine both. I'm happy with stochastic processes, but continuously through time. And that's a deep part of the explanation of how earlier events can be causally relevant to later events through this continuous process. My understanding, which Jacob can now correct, is that he's going to go for a theory where that isn't true anymore. And I'm a bit puzzled about because it's such a big step, right? It's such a huge step. I'm not even quite sure how you represent laws without a continuous evolution. I mean, there's all kinds of issues. But I just wanted to say, when we talk about the Markov condition, which is a fancy word probably a lot of people never heard of, it's just the idea that earlier events can only be causally relevant to later events via intermediate events, right? So that's just the thing I wanted to get clear about.
Thanks, Tim. Markov, just for the record, was a person and introduced a certain kind of matrix in, I think it was 1906. And that's how the name Markov has gotten into this whole story about probabilities and stochastic development and so forth. So I wanted, before I answer Tim's question, I want to clarify something that is a subtlety that was certainly difficult for me in working on this project. And this is the problem that there's a lot of terminological collision that one finds between different topical areas. So, and Tim's question was perfectly phrased. There's no question there. But I do think that a lot of people who may be listening to this might benefit a little bit from just disentangling some terminology. Words like Markov or non-Markovian, words like latent. We'll talk about latent and hidden. We'll even talk about the word model, and even the pictures that are sometimes used. Words like indivisible. These are words that have conceptually different meanings in the theory of causal modeling, the theory of stochastic processes, and in quantum theory. What makes this extra confusing is even some of the diagrams people draw, these directed diagrams, often look very similar in the theory of causal modeling and the theory of stochastic processes. I can tell you this was an endless source of confusion for me trying to understand what had been done in the research literature. A causal model can have what's called the Markov condition or the causal Markov condition, and it can be related to a stochastic process that is not Markovian. And a Markovian stochastic process can be related to a causal model that fails to have the causal Markov condition. So this is all going to be, and there's no way around just disentangling this terminology. So I want to be very precise. One of the things that I really enjoy about talking with Tim is that Tim appreciates the importance of being very precise about things. So let me first just quickly talk about the causal model question. So if you pick up a book like Judea Pearl's classic 2000 book on causality, he introduces his extensive, beautiful theory. It's practically very useful, and he talks about causal models. So causal models are relationships between I guess, features of the world. They're often represented by variables, and these variables are connected together with causal relationships, directed causal relationships from causes to their effects. And often these causal models are depicted in graphical form. One indicates the variables, the features of the world, with what are called nodes. And a node is like a circle or a bubble. And then the nodes are connected by line segments with arrows on them. They're called directed edges. And so you get what's called a directed graph. Often people will impose further that this is a directed acyclic graph, which just means the arrows don't come all the way around, which would be like a snake eating its tail or some kind of weird causal loop. Now, to be clear, also, you can consider models where there are loops if they're feedback loops, but then you have to, it's complicated. If you're thinking about the variables, looking forward in time, for example, usually you want the arrows to not go loops.
Can I just say a word there again so people don't get confused? The kinds of feedback loops you're talking about are between generic things, not particular things. Yes. So, an A-type event can then affect the B-type situation, which then feeds back to an A-type event. But when you're talking about particular events, if you put in cycles, you got retrocausation. You're saying the future can affect the present, blah, blah. That's an entirely different deal, right, than the kinds of feedback loops you're talking about, which could happen in radios or, amplifiers and microphones or whatever. Yeah.
So for example, in the chicken and egg problem, chickenness and eggness are in a feedback loop. But any particular chicken is not in a feedback loop with the egg, right?
Yes.
Chicken lays an egg, the egg doesn't lay the chicken. Okay.
Yes.
So yes, like I said, you can get very precise about all of this. Okay, so we have this picture. We have nodes that represent the variables, and we've got these edges that represent causal relationships. All of the arrows that directly go into one node from other nodes define what is called parenthood in these models. We talk about all the nodes that directly have arrows into a variable. We call those the parents of that node. And the causal Markov condition, precisely stated, says that once you've fixed what's going on with all the parents that directly lead into a node, then that node cannot have any statistical dependence on anything else except maybe its descendants, the things that it has arrows into. This is called the causal Markov condition. And if your causal model lacks the causal Markov condition, meaning that there are extra correlations or statistical dependencies that are not screened off by fixing what's going on with the parents, then the usual attitude is to look at this model and say, we're missing something. There's some latent or hidden structure that we're not observing. And if you pick up Judeo-Pearl's book, you look in section 2.9.1, he talks a lot about this importance of, if it's missing the causal Markov condition, usually you want to go look for what's missing. And the thing that's missing may not be readily observable, but it's probably something that has a physical significance. Some connection that we didn't see. And if we knew what it was and we could put it in the model properly, then the model would obey the causal Markov condition. So that's called the causal Markov condition. Now, separately, we'll talk a little bit about the theory of stochastic processes. A theory of stochastic processes is a statement about some kind of system or object and how it changes with time. And there's a formal way you can talk about stochastic processes using time index families of random variables. We can get very technical, but I want to just use it for now, a very pedestrian view. It just describes how things change with time. Some rule for how things change with time. A list of things, numbers if you want, over time is called a time series. And if we allow the thing at each time to be a variable, then we call it a stochastic process. And for a stochastic process, it may be the case that configurations of the system at previous times play some role or part of the law that fixes either the next state of the system or fixes what its probabilities are going to be. If the next state of the system, the next configuration of the system, or a suitable probability distribution for the next configuration of the system, if the laws prescribe that they are fixed or determined solely by the previous configuration. I mean, it gets a little complicated if you've got continuous time, but we can talk about the subtleties there if you want. But basically, if you only need the previous time for the law to then fix either the next configuration or at least a probability distribution, we say that this is a stochastic process that obeys. You could call it dynamical Markovianity if you want to distinguish that from the causal Markov condition at a causal model. If that's not the case, if it fails to be the case, then we say it's a non-Markovian stochastic process. And you can construct stochastic processes that are not Markovian but satisfy the causal Markov condition. An easy way to see this is just take the parent nodes to be whatever previous configurations you need for your system. And once you have enough of those previous configurations and you know them, that will determine the next configuration of the system. It'll screen off everything else. And then it satisfies the causal Markov condition. So Judea-Pearl might look at this and say, no problem. I mean, if we didn't have a causal model that obeyed the causal Markov condition, but we could include a few past states of the system, now we have a causal Markov condition. Now with these additional variables in the past, we stick them in the causal model, and now the causal model satisfies the causal Markov condition. The parent nodes representing multiple previous configurations system are enough to screen off any other influences. And on the other hand, you could have a Markov process where you only need the previous state in time for the law to then determine the next state or the probability distribution. But it could be that each configuration is some large collection of variables that have weird correlations between them that aren't screened in any way. And if you try to write that as a causal model, it might not obey the causal Markov condition. So I know this sounds very technical, but it's really important to make clear that there are these conceptual differences between things. When I talk about the status of the Markov condition, I'm talking about the status of the Markov condition at the level of a stochastic process, not necessarily the level of a causal model. However, there is a very interesting relationship between the two. So it's not that I'm saying, let's take a causal model, some beautiful, elegant causal model that satisfies the causal Markov condition. And by the way, the wave function or the thing it refers to, the quantum state. And I should say, by the way, just to be clear, when I said quantum state, I did mean the mathematical quantum state. And Tim is right. I was saying quantum state to refer broadly to whatever ingredient, either in the Hilbert space, and it could be what's called a density operator or a rank 1 density operator or a single vector, or the quantum state could be what's called an element, a positive normed linear functional in the dual space to a C-star algebra. There's many ways to talk about the mathematical quantum state that get more and more abstract. But if you want to think of the quantum state as its physical thing, the referent, the physical referent, the thing being referred to by the mathematical quantum state or the wave function. So you might imagine, so I took some causal model that satisfied the causal Markov condition. It had the quantum state in there. It's all great. And then I, Jacob, came along and just ripped the quantum state out of it. Now the model doesn't have the causal Markov condition. Now it looks ugly and complicated, and Judea-Pearl would say, don't do that. That's actually not what I'm doing. So to explain what I'm doing, it would be helpful to tell a few stories, but this would be a good point to pause for just a moment, because I want to make sure that...
Yeah, actually, so let me also make a kind of conceptual comment, if for those of you playing along at home in your own minds. There's causal modeling literature, especially linear causal models, which are very useful for various purposes. I was using that literature to illustrate screening off and the relevance of screening off to causation. But I'm thinking in terms of, I have this very impractical but nice chance, like all physicists, to say, well, ultimately, it's like you ask, what were the causes of some event? Ultimately, everything in the past light cone, or the entire state of the universe, that's the cause, right? Because why? Because I kind of have to specify all of that to give me something that my equations have traction on, my physical equations have traction on. Now, from a practical point of view, if you say, what was the cause of the accident? And you say, well, the entire previous state of the universe, that's not going to help you much when you go and have to defend yourself in court. And so we, of course, think of the world as broken down into more localized things that have much more particularized causal relations between them that we represent with these graphs with nodes, these directed graphs in the causal modeling literature. But those are clearly simplifications. I mean, I take it we all agree. Those are simplifications. They're illustrative for conceptual purposes. What we really want is to get down to the physics of it. And that may well be global, where the causal graph of it is very boring. It's just, it's, the entire state creates the entire state, creates the entire state, or whatever. But you can still ask there, but gee, does it screen off, right? Does a later state get screened off from the further pass by a state between them or not? So yeah, I am thinking in terms of the stochastic process notion that you have in mind. I illustrated it because I think there are people who don't follow physics who may be familiar with the causal modeling literature, and there are kind of conceptual connections that are close enough to give you a feeling for what's going on. That's all.
I have a question actually for you, Tim, about this. So
yeah.
In my experience, analytic philosophers, philosophers of science, philosophers of physics seem to be very familiar with causal modeling. In fact, I would argue, and I think I argued in a previous conversation with Robinson, that one of the most fruitful relationships between science and philosophy is between statisticians and people who work in statisticians and philosophers, but especially statisticians who work in things like causal modeling. I mean, you read Judea Pearl's book, for example, and it's filled with lots of discussion of actual philosophers, Nancy Cartwright, David Papineau, and various people. But Tim, in your experience, do philosophers have a lot of familiarity with the theory of stochastic processes? That has not been my experience.
Okay. Right. So this is a little inside baseball, but just so people know, my dissertation advisor was Clark Gleamore. Clark was doing work on causal models and causal search. Wonderful book. This actually, Pearl learned a bunch of the stuff he writes about from Clark and Peter Shyness and his students. So I'm familiar from there, but when I was in graduate school, Ken Schaffner was interested in medical methodology and in causal models in medicine. So of course you got used to it there. And Nancy Cartwright, sure, a lot of people who are not doing physics, but are looking at the special sciences where you have these simplifications, are very familiar with linear causal graphs and causal modeling there. As far as stochastic processes go, okay, when I got out of graduate school and came to Rutgers, I met Shelley Goldstein, who had been working on Nelson's theory, and so he was awash in stochastic processes. So I got kind of familiar with stochastic processes myself very early. I guess the people who work on pilot wave theory are kind of aware that you can do stochastic versions, like Nelson's stochastic mechanics. So I think a lot of them know at least the basics of it, but that may be a little niche.
Yeah,
I mean, that would be more niche than knowing about causal modeling.
Right. That's been my experience, that it's sort of, you find it sparsely distributed.
Mm-hmm.
I should say that the connection between stochastic processes in physics is also very complicated. I think I may have mentioned elsewhere, again, maybe Robinson, you and I, when we talked, that in Hugh Everett's thesis, he talks about some work, this thesis he's writing in 1956, 1957. He talks in his thesis about Fritz Bopp working on a stochastic process interpretation of quantum mechanics. That was an early forerunner to what we would now call Nelsonian stochastic mechanics. These are all based on using things like Brownian motion, Wiener processes, inherently Markovian type stochastic processes. When I speak to physicists and I say the word stochastic process, or really myself, because I was trained in philosophy, but also in physics, when I thought of stochastic processes, I always thought of Markov chains, Markov processes. The idea that a stochastic process was inherently Markov was just always taken for granted in my experience among many physicists. Now, I'm sure there'll be people watching this saying, I don't take it for granted. It's true. There are absolutely some situations people don't take it for granted, but broadly speaking, in my experience, it was. So you get kind of a tunnel vision, and it's very hard to see what else could be there. Let me quickly address a point that Tim very, very sagely made, which is that when we're doing causal modeling for macroscopic, everyday stuff, medical stuff, cigarette smoking, and so forth, the causal Markov condition is extremely important. It's very important for causal discovery. It's very important for how we think about what's going on ultimately. We, of course, have very, very little experience with the structure of causation when phrased solely and directly at the level of the atoms of nature. And Judea Pearl, I should add, is quite upfront about this. In fact, he even introduces a word. He says maybe at the level of quantum mechanics, we need to replace causality with quausality. And he doesn't know what that, and he says in the section on latent structures, he's like, I don't know if this generalizes all the way down to the microphysical regime of quantum mechanics, but certainly it's got to somehow emerge from macroscopic stuff. So what I'll tell you is that although I don't take a causal model and just rip the causal Markov condition out of it, the causal models that will emerge at the microphysical level of the atoms, I say atoms here metaphorically, the level of whatever the mereological smallest components are, will not initially have a causal Markov condition, but it emerges in the macroscopic limit, which is when we need it. So that's farther downstream. Let me start with a story. It's one of my favorite papers, and I know Tim knows this paper. It's actually one of the first papers that used the phrase temporal action at a distance. Not the first paper. I think the first paper I was able to find was a paper by Arthur Papp, I think from 1952. But the paper I'm referring to is a paper by Sidney Shoemaker, 1969. And the paper is called Time Without Change. And Shoemaker is trying to answer a question, a very old question that goes back to antiquity. Are expanses of time, do they necessarily correspond to changes in physical ontology? Does it make sense to say that you could have some expanse or duration of time, but nothing is different from one part of that expanse of time to the other, the level of the physical ontology? And the, I guess, gut impulse one might have is, of course not. How could it make any sense? And then Shoemaker asks, could we have any good empirical reason to think that could be possible? And you'd say, well, even if you thought metaphysically, and here I'm using metaphysically in the colloquial sense, not, I just mean in the sense of, beyond, maybe beyond empirical, whatever, but how could we ever have any empirical evidence that there was a stretch of time in which nothing changed? That's impossible. And he says, well, how about the following scenario? And I'm going to change some of the numbers a little bit, because I like these numbers a little better than the numbers that Shoemaker used. I think they're a little more evocative for a variety of reasons. But roughly speaking, this is the picture that Shoemaker describes. Because I think people listening might go, this is ridiculous. How could you ever have empirical evidence? But just hang on. Shoemaker says, consider a hypothetical different world or universe. Just a hypothetical other universe. And this universe is some expanse of space, some featureless, enormous, infinite, whatever, no boundary, just huge, empty space. And the only thing in this universe is 3 civilizations that are separated from each other in space. They're all like in some compact region. There's a compact region for one of them called that Civilization A, and some large distance away, there's a compact region where Civilization B lives, and then some large distance away from the other two, there's another compact region where Civilization C lives, and it's empty space in between. Each of them is like a little island in space with, maybe it's like a planet or something like that, but there's basically nothing between them at all. And these civilizations, they know about each other. They're not so far apart. They can look in telescopes. They can see each other. And, well, civilizations B and C, they notice something rather odd. They notice, and I'll just say for the sake of simplicity that, I guess they're all orbiting a star or whatever, their own star. They have a notion of the year. But civilizations B and C look at civilization A and they notice that every 7 years, Civilization A just freezes. Like, they're doing their thing, the people are talking, and then everybody stops. Everything stops. There's no motion, no activity. Just everything has come to a halt. Brain activity, perception of everything is just frozen. And it remains frozen for 1 year. And then at the end of the year, everything just starts moving again. And none of the inhabitants have any memory or perception that there was a gap in time. And civilizations B and C notice this happens every 7 years. They're like, that's funny. They don't seem to be any worse for, the trouble. So, okay, I guess that's just the way things are. Civilizations A and C look at civilization B and they see that every 11th year, The same thing happens to civilization B. It totally freezes for 1 year, and then it unfreezes. Okay, that's weird. And I say freeze, I don't mean it gets cold. It just everything stops and then it starts again. So no one is hurt. There's no harm to anybody. And again, all the inhabitants of civilization B have no perception that there was a gap. For them, it was just like they jumped over that year with no perception of the time in between. And then, of course, obviously, you can see what the story is going. Civilizations A and B, they notice that civilization C has a similar pattern, only it happens to them every 13th year. Every 13th year, they go through a year. They're frozen. This somehow reminds me of cicadas. I don't know why, because cicadas, you may know, there's a certain kind of cicada that only comes out every 13 or every 17 years. And it's one of the rare cases where prime numbers show up in the natural world. And there are all kinds of conjectures about why this is, trying not to sync up with predators maybe, or not trying to there's all these theories about it. But we just noticed that prime numbers show up in this case. So somehow this story reminds me of cicadas somehow. Okay, but then there's an interesting question you can ask. So 7, 11, and 13 are prime numbers. That means their least common multiple is the product of the three. And you can do the math. The reason I picked these numbers is I wanted a very big number, but also it's very nice. 7 times 11 times 13 is 1,001. It's nice. It's a really nice number. And so what are they to make of what should happen on this, on the 1,001st year? I mean, if you just look at this, you'll go, well, I guess the 1,001st year, they should all be frozen for a year. But of course, none of them have any experience of that. They're all frozen. None of them have any memories of that. So do they have good empirical reason to believe that they are in fact all freezing on the 1,001st year? Or should they have a more complicated model of the world where every 1,001st year, the usual rules don't apply and there's no freezing? Like, what would be, if you were an inhabitant of this civilization, what would be your guess? You'd probably say, it does seem kind of plausible that we are in fact all of us freezing. But of course, if we all freeze for 1 year and we're the only things in the universe, the only physical ontology in the universe, then are we committed to the idea that there's a duration of a year in which there is no change to any of the physical ontology? And I just think this is such a beautiful example, because who would have thought there could be any good reason to think that this could in fact be going on?
Yeah, I mean, can I just make a comment here? Some of this goes back, of course, to Aristotle, who says time is the measure of change.
Right.
And
that's what I meant by
antiquity. That's right, but it's also the case that time is the measure of stasis. Right? If something's not moving, you still say there's a certain period of time. It has to be not moving for a period of time, or else it's not stationary. And so time is also the measure of stasis. Now, I'd say, yeah, but if all the clocks have stopped, we could never know that things had frozen. And now, and this actually is a bit relevant to Heisenberg and so on. You think when Heisenberg, 26, we're about the time of logical empiricism, there was in the philosophical world, in the Vienna Circle, a very strong push to this idea that you need to reduce all meaningful language to observation language, right? To the protocol language for philosophers who know this stuff. And that you just couldn't even have meaningful language that went beyond what was observable. And people thought this was the moral of relativity. Actually, don't talk about space and time as things in themselves. Talk about instruments, clocks, and how we use them, and this kind of instrumentalism. There's a wonderful story that Heisenberg himself tells, that he gave this talk on matrix mechanics in 1926, University of Berlin, and Einstein came, and he was so interested that he walked back with Heisenberg. And Einstein says, Heisenberg, you can't be serious. You said that, you talk about electrons, but, and being in atoms and their motions, but then you say the theory must be formulated in terms of what's observable. He says that doesn't make any sense.
Right. There's a famous line here, right?
And he says it's the theory that tells you what you can observe, right? You have to understand the theory and then analyze it to see what the observations will be like according to the theory. right? And Heisenberg says, but Einstein, isn't this what you taught us with relativity, is that we have to think? And Einstein says something like, well, maybe I said stuff like that, but it's nonsense all the less, nonetheless. It's the theory that tells you what you can observe. And this then chimes, you have to jump from the Vienna circle up to Quine and conformational holism, and this idea that, look, yeah, we could have evidence. I mean, I don't really care whether yes, we were frozen for a year, or there was a weird glitch that it changed all the rules. Which one is more plausible? The point is, they're both things you ought to consider. I personally think that we were frozen for a year would be the better, but okay, I don't want to argue about that. But the point is that you have to take the entire situation and the entire theory and all of the observations and all of the explanations into account to make judgments of scientific plausibility. And what Shoemaker gives you a case where even the empirical data, together with very plausible assumptions, would lead you to the conclusion that everything froze for a while, right? That time went on with the physical state unchanging. Now, to come back to your first point, this would require a kind of temporal action at a distance, because somehow after a year, I mean, why do things start up again, right? There can't have been any immediate preceding cause because everything was frozen, right? So you would need a kind of temporal action at a distance. And I'm not saying it's not inconceivable. It's not self-contradictory. It's not a feature of any physics we've had, and it doesn't seem to be a feature of the world we're familiar with. Anyway,
it's great, and let me just say for people who'd like to read this story, which is a fantastic story, it's in Physics and Beyond, Heisenberg's book, his sort of memoir book about his life. I highly recommend it. It's and the details of that engagement between him and Einstein are really very interesting. So you Tim, exactly, you're exactly right. Shoemaker talks about temporal action at distance because in a universe like this, it's the most natural way to describe what's going on. If you ask, does the configuration of this universe 1 second before an unfreezing, is that enough to predict that it will unfreeze? The answer is apparently no, because every second during the 1,001st year that's frozen appears to be ontologically, physically like every other second. And just from knowing the configuration at one of those seconds doesn't tell you that this is the last second. You somehow, it would seem you'd need more information. Now, there is an alternative, right? You could think of this as, we wouldn't exactly call this a stochastic process because it's not really probabilistic. It's a trivial version of a stochastic process where there's no probabilities, but it's a dynamical process for sure. There is an alternative. An alternative is to turn it into what's called a hidden Markov model. In a hidden Markov model, you introduce formally some additional variable. You introduce some variable to the model. This variable is sometimes called a latent variable or hidden variable, and this is the other distinction I want to make between stochastic processes or dynamical processes and causal models. So although the same term is used, hidden or latent, it's not quite the same thing. In a causal model, like I said, you restore the causal Markov condition by introducing some latent variables, but you think those latent variables are probably representing something physical in the world. For a stochastic process, turning the process into a hidden Markov model means introducing some new variable, and with that variable, we can model the process as if it were Markov. The additional variable enhances the process to being a Markov process. But usually in the stochastic process literature, this hidden variable is not treated as some physical object or something like that at any given time. In fact, in a lot of models, it's explicitly taken to be a summary of the entire history, but just like stored up as one variable. This is what's more typical to view what we do with a Markov model. But let's just take the universe that we were describing, the Shoemaker universe, the cicada universe, if you want to call it that. Let's suppose that I formally augment this picture with a new variable. This new variable is not located anywhere in space. It's not local. It's some non-local. It's maybe exists in some sense, but it's not fixed anywhere in space. And this variable is just like an increasing variable in some sense. It simply increases with time. Now, if we have this variable available to us, then we can write the laws of this universe in a Markov way very easily. If you want to know what's going to happen to a civilization, you just consult this variable, right? You can't see the variable. The variable is not visible. It's unobservable, but it's not unobservable because it's small or complicated the way maybe a latent variable in a causal model might be. It's unobservable in principle. It's not something that has any kind of existence in the familiar sense that it is located anywhere that you could see it. But if you believe it exists, if there is a Schrodinger, let's say, in this universe who says, I can turn this strange set of laws that don't appear to be Markov, I can make them Markov by introducing a new unobservable ingredient of reality that isn't really located anywhere. Well, then you're going to get a Markov description, right? That variable at any given moment will determine what the universe is going to look like. There are a couple of interesting features of this variable that we've introduced. One of which is that it's not located anywhere. And the other is that it's not back reacted upon by any of the physics. The lack of back reaction is a really telling feature. So this extra variable we've introduced, this non-local clock, seems to be determining what's going on to the universe, but nothing going on in the universe in any way appears to be able to do anything to the clock. The clock does its own evolution and sort of reaches down in some sense to the universe, if you want to imagine it's there. There's no back reaction. So the lack of back reaction is a very telling feature that you have as a hidden Markov model. So this is, and of course, one of the things that one will note in a theory like the Bohm theory, which has the wave function as a part of the physical ontology on some readings of the Bohm theory, and also has local ontology, the beables, the things that can be, in simple models, the particle arrangements. You have both of these things. It's notable that the pilot wave doesn't live anywhere in physical space. It's non-local, and the particles don't back react on it. And this is very reminiscent of what goes on with the hidden Markov model. So before I go any further, this would be a good place maybe to pause. I want to, in a moment, present a very simple model that will motivate the indivisible theory. But let me just stop there for a second.
Yeah, I mean, I think it's a good place because, otherwise I'll just sit here and stew for a while. So let me get it off my chest. So just a couple points. One is this idea that there's no back reaction. In the standard pilot wave picture, that's true. That is, you have the quantum state. It evolves always by Schrodinger evolution. And that's it. You don't need, there are these particles. The particles are moving. The particles are being piloted or guided by the state of it. But there's no back reaction. This has been a complaint forever, especially from the many worlds people. It violates Newton's third law. Blah, blah.
I'm not complaining, to be clear.
Yeah. Okay. I'm just,
yeah.
But you think it's significant, right? You think it's suggestive.
Suggestive, perhaps.
Okay,
better.
let's put it that way.
Yeah.
And I just have a couple comments to make. One is, if you want a back reaction, you can put it in. I mean, I actually mentioned back reaction dynamics a while ago in a conversation I was having with David Albert and some other. He said, "What's back reaction?" I said, "Well, that's something I just made up, where you add an extra piece to the Schrodinger evolution that is a function of the configuration. Maybe it slowly kills off the empty branches, right? You can imagine doing it if you're that, head up about it. You could do it in a way that would probably be empirically unobservable."
Do you want to just say what empty branches are, Tim?
In the pilot wave theory, it's just the branches that are parts of, as it were, associated with parts of configuration space that is not anywhere near where the configuration actually is. That's what that means. That's
because it's a term of art. I want to make sure people.
Oh yeah,
listening.
okay, yeah. And in a collapse theory, the collapses will essentially kill them off. I mean, not completely because you use a Gaussian blah blah, but reduces the amount, the magnitude, the amplitude of the wave function away from where the collapse center is. You could put a term in that kind of slowly evaporated off the parts of the wave function far from the actual configuration in a pilot wave theory, if you were so inclined to. I can't, I'm not concerned enough about this because I never thought that this analogical version of Newton's third law was anything I should pay attention to. I mean, I think, as it were, in a way, the laws of physics influence the particles, and the particles don't have a back reaction influencing the laws of physics. So at this analogical level, I was never worried about that. But I do want to say, you introduce this as I'm introducing maybe even self-consciously a fictitious object, and the way you described it made it sound pretty fictitious. Whereas when I started, I said, look, we need something that actually does evolve by a wave equation, because we have actual phenomena that are interference phenomena. I mean, there's this comment that Bell makes about the two-slit experiment, where he says, is it not clear from the smallness of the scintillation on the screen that we have to do with a particle? And is it not clear from the interference that the particle is guided by a wave? Now, that wasn't to make it Markov or anything else. It's to say, we know the kinds of physical systems from classical physics that display interference phenomena, and they're governed by wave equations, and the wave equations are Markov processes. And so if you just go that way, you're going to get a Markov process. It's going to be written down as a continuous, differential equation in time, which is kind of what we want, what we've always had. So I think it would be misleading to suggest that the motivation of Schrodinger, or a pseudo Schrodinger, was just, gosh, I really want Markovianity. I better put this new thing in to maintain it. The straightforward motivation was, gosh, I've got an interference process. I better have something governed by a wave equation. Now, it turns out it can't just be in physical space. It has to be in this higher dimensional space, and that's connected with entanglement, and then that eventually with non-locality. Again, this isn't just on a whim. I mean, this stuff is being introduced for really very good empirical reasons. So I think if someone listened to the account you gave of how this new thing gets in, they'd say, gosh, somebody really is so attached to Markovianity that they're willing to postulate whatever to maintain it. But I don't think that corresponds to the history, or certainly not a rational reconstruction. Of course, I'll just say one final word. When we rationally reconstruct quantum mechanics, we often start with the two-slit experiment. They didn't, right? They were talking about spectra and, light coming off of atoms, and that leads you to matrices, and that leads you in a certain direction. If you start with two-slit interference, it leads you in another direction. But I think given where we are, starting with the two-slit thing gives you a smooth story, plausible story about why one would not only do this, but hard to see how you could do anything else.
So let me just say a couple of things. The first is, of course, in the Shoemaker universe, our parallel world Schrodinger could certainly introduce some back reactions on the clock variable. I mean, that would certainly be fine. If you have some problem with the clock variable, you can deform it lots of ways. There are a number of other telling features that I want to call some attention to. One is that the clock variable we've introduced is not just abstract and non-local and doesn't get back reacted on the simplest Markovian model, but it's also highly malleable to redefinition. For example, we could make our clock variable periodic. We could say that every 1,001 years it returns back to zero. It's like really a clock with 1,001 years and then it returns back to zero, a modular clock. There are much more radical things that we can do to it, and this will become much more apparent once we start considering generalizations of the Shoemaker universe in which there's probability. So I'm going to come back to that, to those points in a moment. The next thing I just want to point out is, Tim, you're completely right. Schrodinger didn't sit down and say, we need to make a Markov model. I'm going to introduce a fictitious thing to make a Markov model. That's not what Schrodinger did. You're completely correct. You can read go back and read the papers. They're beautiful. The first few were in German, but one of the seminal papers that Schrödinger wrote in 26 was in English, because he spoke and wrote in English as well. It's a beautifully written paper. It's where he introduced, he talks about the undulatory theory of mechanics. I think undulatory is a much better word than wave. It's such a lovely word. And he makes clear that his motivation is coming from the Hamilton-Jacobi formulation of Newtonian mechanics. Now, I don't want to get too in the weeds here, but a couple of salient things are worth saying about this Hamilton-Jacobi formulation. In the Hamilton-Jacobi formulation of Newtonian mechanics, for at least some kinds of Newtonian systems where we can represent the forces in terms of what are called potentials, there's a whole story there. There's a way to rewrite the laws of Newtonian mechanics. The laws of Newtonian mechanics take the form of a kind of not quite Markovian set of laws. They're second order in time. And second order in time laws are slightly not Markovian. You need to know the configuration of all the particles now, and like slightly earlier, and the slightly is in the sense of a calculus limit, in order to get the configurations that are coming up. Now, there are various ways to rewrite this story to make it look Markov. There's the Hamiltonian formulation, which looks more Markov. We can just take velocities to be fundamental aspects of reality. There's various things we can do. The Hamilton-Jacobi formulation writes the laws in a Markov way, in a rather curious way. There's a long story to how you get here, and I can tell you all the details if people here would like, but the upshot is you end up with a couple of equations that are all explicitly first order in time, explicitly Markov. These equations describe the evolution of an abstract function that's not local. It doesn't exist anywhere in space. It's in fact defined on configuration space. It is not back-reacted upon by the particle. And this function is called the Hamilton's principal function, or the Hamilton-Jacobi function. And you solve a partial differential equation that looks a lot like, technically it's called an iconal equation. It's very similar to a wave equation, but it's a partial differential equation. And then the gradient, the mathematical gradient of this Hamilton-Jacobi function determines the momentum or the velocity of all the particles, which is like a guiding equation. And you could have imagined people writing this down and going, oh my gosh, maybe this suggests that the best way to think about Newtonian mechanics is that there's this new entity, this non-local entity that exists. It's ontological. It's this Hamilton-Jacobi function, and it guides the particles around. Everything is now first order. We have a first order velocity guiding equation. I think most people from a Newtonian persuasion would have said, no, the fundamental physical picture is this second order dynamical equation. And really we're just finding a very clever way to reformulate it to make it look explicitly Markov, to give this very elegant picture with guiding and first order velocity equations and so forth. And although Schrödinger didn't talk about, this was before Bohm, this is before even de Broglie, who had a somewhat similar theory.
It was after de Broglie.
Look, this was 26. De Broglie's theory was 27.
De Broglie's even got the idea in 23, presents it, I think, in 25.
But the pilot wave model? Explicit with guiding equations? Wow, I didn't know that. I thought he presented that after Schrödinger. So I know that de Broglie had, his matter wave hypothesis that came first, and it was his thesis, and Einstein, and he won a Nobel Prize for it. His 1924 thesis, he won the 1920
Maybe look, I remember someone telling me it actually went back anyway.
I wasn't aware of that. You could be right. I'm not an historian. But certainly Schrödinger's writings don't betray that he was thinking about particles being guided or anything like that. But he did use the Hamilton-Jacobi picture. He took the Hamilton-Jacobi function that satisfied this partial differential equation, and he said, well, it satisfies a partial differential equation that looks like someone took a high frequency or iconal limit of a wave equation. If that were the case, what would be the wave equation, and how would the Hamilton-Jacobi function fit into it? And what he did was he essentially exponentiated the Hamilton-Jacobi function. He regarded it as the phase of a wave. And in fact, he drew these beautiful pictures. You can look in the paper. He draws what are called the level curves of the Hamilton-Jacobi function. And he shows how they would change with time, and it looks like wave fronts. But this is all happening in Newtonian mechanics. He hasn't gone to so you're seeing wave-like stuff, not empirically, but at the level of the mathematical formalism already in the Newtonian case. And this inspired him to propose maybe the Hamilton-Jacobi function is the phase of some wave function. He introduces this trident symbol. This trident symbol is a wave-like function for which the Hamilton-Jacobi function is its phase. Like the Hamilton-Jacobi function, it lives on configuration space. It's not defined in any local sense. And then it evolves according to the wave equation. And then by looking at the so-called like normal modes of this equation, he was able to relate that to the energy values of atomic spectra. That's how he arrived at this. And so although he wasn't saying to himself, I need a Markov description, the way that he arrived at the wave function by building it, constructing it out of something that a Newtonian probably wouldn't have regarded as a part of the ontology is also, I think, in retrospect telling, even though it wasn't, I think, part of Schrodinger's thought process at the time.
Right. So let me just make two quick comments about this, because you said something that's technically correct, and I just want to explain exactly what you said. Well, Newtonian mechanics is almost Markov, but in a way, not quite. And the reason for that, as probably everybody knows, is that in Newtonian mechanics, the initial conditions you need are both the initial positions and initial momenta or initial velocities of all the particles. So if you say, well, just give me the state of the entire universe at a moment, then you have to stop and say, well, what do you mean? What's true of it at a moment?
Laplace versus Boscovich, right? Yeah, this is great. Yeah,
exactly. You might say, well, certainly the positions are all what they are, and so the configuration is all what it is at a moment. But what about the velocities? Are there instantaneous velocities? There's a big philosophical literature about the conceptual possibility of instantaneous velocities. Do those exist at a moment? They're pegged to a moment, right? You can, as it were, if the velocity is changing smoothly, you can ascribe a velocity at a moment, but you might say metaphysically, you need more than a single moment for there to be a velocity, right? So that's true because Newtonian mechanics is a second order theory in time. That is, the fundamental dynamical equation is about accelerations, which is the second time derivative. So you sort of, one way to think of it the way Boscovich did, which is right, I need a little sandwich. I can't just take an instantaneous state. I need a little sandwich of time, but it can be as thin as I like, right? I can make it as small as I like. That'll give me all the derivatives up to any number of derivatives. So if that's the difference between a really Markov and quasi-Markov, that's true. But notice, and this is interesting, that in the pilot wave theory, you don't have that problem at all, because the two fundamental equations, Schrodinger's equation and the guidance equation, are literally first order in time. They're just single derivatives with respect to time. So really, in that theory, you can say, just give me the state at a time in terms of what we would call categorical facts at that time. If the wave function represents a categorical physical fact, and the configuration represents a categorical physical fact, and that's it, right? Any information about what happened earlier, you'll be screened off, right? It won't give you any more predictive power to know anything more, right? So that actually suggests, at least if you're going in a pilot wave thinking, that this is more Markovian, right? It's more friendly to deep Markovianness than even Newtonian mechanics is. The second point is, everything you said about Hamilton-Jacobi theory is certainly correct. The motivation is a lot of the mathematics that was used. It was familiar to people. They had it to hand. The thing I started with the two slit experiment was the interference phenomena, right? That you can have both constructive and, more importantly, destructive interference. That just looks like wave behavior. I mean, in a serious way. And that if you have a quantum state represented by the wave function evolving by a wave equation, that you would get that kind of interference is what you'd expect. I don't know of anything in Newtonian mechanics that would be analogous to that. right? So I can see why the Newtonians would say, yeah, this is some nice abstract mathematics. At the end of the day, it all boils down to F equals ma. Um, but trying to say, well, how do I account for these interference bands? That's just a straightforward physical problem that the tools they had available are just suggestive of a wave phenomenon. Yeah.
Yep. No, I'm so glad you brought that up. I don't know if you can see my chalkboard from behind me, but you may see that I have a double slit experiment on my chalkboard. This is definitely something that we're going to talk about. So I agree with everything that Tim has said. It's not if you try to make an analogy to Newtonian mechanics, you have at a mathematical level, and I made clear to say this, something that looks kind of wave-like. The Hamilton-Jacobi function looks like wave fronts. It has a distinctly wave-like nature. We would call it the geometric optics limit type sort of iconal approximate wave-like nature. But in Newtonian mechanics, we don't see empirically signatures of wave-like behavior in experiments. Now, the double slit experiment has a long vintage, right? I mean, the original Young double slit experiment was, and now I'm not an historian, but my understanding was that it was part of a debate over the nature of light, whether light was made of Newtonian classical particles, the corpuscles, the corpuscular theory of light, or that light was inherently a wave. And the Young double slit experiment involved sending light through two slits and seeing an interference pattern. And that helped cement the idea that one should think of
really
waves.
Originally the thing that's sometimes called the Fresnel spot and sometimes called the Arago spot and sometimes called the somebody else spot, which you probably know the story. I mean, it's an amazing story because Newton had a corpuscular theory of light in the optics. There was a contest that they announced for that they did back then, and who was it sent in the wave theory, and then I can't get the players straight. One of the judges said, no, this is crazy, because if this wave theory were true, you'd see this funny spot. If you had a source of light and then a circular barrier, there would be a bright spot at the middle of the shadow, and that's crazy. And then they did the experiment and found it, right? And then you go, I guess wave mechanics is correct. I guess the wave theory of light is correct, because this was a prediction of the wave theory that was thought to be an absurdity, but actually showed up. It's a great story. I wish I could remember the details of all the players.
I mean, to situate this, of course, this is centuries ago. The Young double slit experiment was not recent. There is a little bit. Is it okay if I do a little bit of a tangent that I think people here will like? And Tim, I think you'll also really appreciate this. It's a little bit of a tangent. So you probably, Tim, I'm pretty sure you probably know this. I'm not sure very many people know. The first theoretical prediction that the sun's gravity could deflect light predated Einstein's theory of general relativity by over a century. In the Newtonian corpuscular theory of light, the idea is that light particles are very lightweight particles. Light now in the sense of mass, right? Very, very lightweight. Famously, Newtonian mechanics doesn't really know how to deal with massless things very well, because then there's nothing that shows up in the Newton's second law. But if you treat particles of light, if you think that light is made of classical particles, just little classical particles flying around, they could fall under gravity the way that other particles could. And Cavendish and Saldner proposed that maybe this could predict that the sun's gravity could deflect starlight, that as the light from stars was streaming at us, if it came very close to the edge of the sun, on its way to us, the sun's gravitational field could bend its path, just like anything could fall under the gravitational influence of the sun. And then when we looked at those stars, we would see them in the sky. If we could, maybe during a total eclipse, when you could see the stars near the sun, we'd see the stars apparently coming from a slightly different location because their light had been diverted. And Saldner did a calculation of how big the effect would be, and he got a prediction. And rather famously, this calculation was done in 1801, I believe, remarkably long ago. And this prediction was almost exactly correct. It was off by a factor of 2.
Of 2, yeah, it's a big factor. It's an important factor.
Well,
that factor of 2.
It wasn't off by a factor of 100. It wasn't, It was a factor of 2, a very curious factor of 2. Now, of course, the experiment hadn't been done, so no one knew whether it was off by any factor. Interestingly, Einstein did the calculation in 1911 with a very preliminary version of his theory of general relativity. And he was motivated roughly by an application, a qualitative application of the principle of equivalence. And he ended up making the same prediction Saldner made in 1911. Oh. And very fortunately for Einstein, no one did an observation of this effect in the years between 1911 and 1915, when Einstein completed his theory of general relativity and found the full dynamical equations. He then redid the calculation on his full theory and got an extra factor of 2, that the deflection should be twice as strong. And he did that calculation in 1915, 1916. And then when the experiment was finally successfully done, the Eddington expedition in 1919, they found this factor of 2. There was some historical scholarship that doubted whether the precision of the experiment was strong enough to make a discovery claim. I've talked to some historians in the last few years, and there seems to be consensus from at least some of them that they just had really good atmospheric conditions, and the results on retrospect were robust. But in any event, that's what rocketed Einstein to international stardom. And that's why now you draw a circle and a wavy line on top and a wavy line below, and everyone's like, Einstein, right? That's what he became, this huge character. But there's a really interesting point about this factor of 2. So you can get the factor of 2 through a very detailed calculation. I assign it. So I teach general relativity at the graduate course in general relativity here at Harvard for like over a decade. And this is a calculation that's a homework problem now. It's amazing how in the history of science you go from things that were huge, apocal discoveries to now just homework problem 3. But there's a really interesting connection of this factor of 2 to an old question. The question about the equivalence of inertial mass and gravitational mass. I know this is a little bit afield, and I'm sorry, but Robinson, I've listened to your podcasts, and sometimes the most fun parts of the podcast are the tangents, the diversions. So I hope everybody is on board.
I've been loving the tangents thus far.
So the thing that when a student takes a course in Newtonian mechanics and they learn about Newton's law of gravity, the student is told, that parameter, that constant proportionality, however when I think of it metaphysically, the inertial mass. I'm sorry, another digression. Inertia. So Robinson, last time we spoke, you asked me for etymology. Inertia is such a lovely word. It comes from, it's the same as inert, which comes from in, not, and ars, which is Latin for craft or make, like creative crafting, making. So inert is to not be doing anything creative, and inertia is the quality of not doing that. Anyway, so, but when a student takes a course in introductory Newtonian mechanics, they learn that the same parameter m, inertial mass, that shows up in F equals ma, that relates net external force to acceleration experienced by an object, is like the gravitational charge, the quality of an object that makes it both actively produce gravitational effects and passively respond to gravitational effects. And that's quite surprising, and it leads to various predictions like that objects that are small enough that they won't tug on the Earth too much, and the Earth we can treat as still, objects will hit the ground at the same time if they're dropped from the same height, because the mass is canceled. The inertial mass in F equals ma cancels the mass in the law of gravity just perfectly. And to Newton, this was a great mystery. I guess technically, it's not that they're exactly the same, but they're the same up to some universal constant proportion that we can absorb into, the redefinition of Newton's.
Can I just?
Yes.
I'm unaware of Newton saying it was a great mystery. I would have thought he would just say there's a single thing, mass.
Maybe.
It shows up in one law, in the fundamental dynamical law, and it shows up in the law of gravitation. Yeah. There's no mystery why something is itself, right?
Sure.
I mean, if you think they're like formally, as it were, different roles it's playing, but you might not think it's a mystery. You might just think, well, the same thing. I've got this physical magnitude floating around, and it does a couple things, right?
Thank you, Tim. You're completely right. That was unjustified. I'm not an historian. I don't know for a fact that Newton commented in that way on it. It is interesting to note, though, that, of course, later we discovered other kinds of charge, like electric charge. that show up in a very similar way in their appropriate force law. The Coulomb law
Right.
of electricity has electric charge that also, objects have, and it produces forces, but the electric charge is not like inertial mass. So it's weird that gravity has this feature. And so what a student is told, the more proper thing is, you go to a class and the teacher says, isn't it a weird coincidence these happen to be essentially the same thing? But that can't be the case in general relativity. It can't be the case that they're literally the same thing, because of course in general relativity, there are massless particles. There's light, and light has has zero. That parameter m, the inertial mass, is zero, and yet light responds to gravitational fields, and light carries a kind of energy, and energy gravitates. So there's clearly something going on here. When you take a course in general relativity or read any of the textbooks, this is basically not really discussed. The equivalence of inertial and gravitational mass in the Newtonian regime is mentioned as one of the motivations for eventually getting to the strong equivalence principles, the weak strong equivalence principle. But then it's like not mentioned, and then you just have general relativity. We just use general relativity. We look at geodesic motion, and we don't really talk about this anymore. But it is a really interesting question. Like, what happens to gravitational mass and inertial mass?
Right.
What happens to them in the full theory? And I don't know, Tim, have you probed this question? Because it's a really interesting
I mean,
question.
I'll say a few comments. Look, we're on fleas at this point, but okay, let's just do one flea down.
Sure.
First, a comment for people who don't know. Not only was there predictions of gravitational lensing, as it were, for light, if you'd had a corpuscular theory, but famously, I can't remember who, calculated the mass of a Newtonian black hole, that is, a star so heavy that by its gravitational mass, light could not escape it. The escape velocity was infinite. Okay, so, you just couldn't get light off the surface of this star.
Just for record, it's John Mitchell.
Okay,
Mitchell, and then Laplace popularized it, but yes,
right.
Mitchell. Yeah.
So, I mean, you can ask these questions. It leads people to have a very mistaken notion of what a black hole is, because there you really do have a very massive object that's sitting there that you could, fly into and crash into the surface of. In a black hole, there ain't no such thing, right? There's nothing there sitting in the middle that you can bang into. So it's a very, but I mean, from my point of view, I guess, once you do the trick of thinking, gee, all these gravitational effects that Newton is explaining via F equals ma and the universal force of gravity, those effects are now going to be explained by the geometry of space-time itself. Then it's trivial that light and everything else that's in space-time, right? All you need is an object that's in space-time and where its dynamics is written down in terms of space-time. It'll be affected by gravity because gravity is space-time geometry. So one part of that kind of goes away, right? The other part is the source part, right? What about a light goes into the stress energy tensor, which is important in solving the Einstein field equations? And for that, we also have to remember this famous quote of Einstein when he says that the field equation is like a mansion, one half of which, the right side, the geometry side, is marble, high-grade marble.
And there's wood.
And the other side, the stress energy tensor side, is low-grade construction plywood.
Yes.
He himself knew that representation of the matter energy content was just a kludge.
Yep.
Right. A convenient kludge, the one that had the right mathematical form to make the equation work.
Right.
And he knew it wasn't right. This is also, he talks about this very nicely. He knew that wasn't right. So when you get to that side of it, but how does the mass energy of a photon influence the gravity, which means influence the structure of space-time? Because what we have is going through the stress energy tensor, already you're in a mess, right? So I don't think there's a general relativistic account of that, because you're getting to the part of general relativity that was never really complete, right?
Yeah. So, but there's some things you can do here. So certainly inertial mass plays a role in relativity. This is again getting a little in the weeds, but we do assign particles in general relativity inertial mass. the invariant, momentum, momentum squared is determines, it's a Casimir determines the inertial mass of the particle. And then, of course, we have gravitating mass. I mean, after all, if in the Schwarzschild geometry, the black hole geometry, but more generally the geometry around any kind of like spherical object, there's a big capital M that plays a certain role in determining the shape of the space-time in the vacuum exterior of a spherical body. And the question is there some relationship between these apparently qualitatively different things?
Now I'm puzzled. The Schwarzschild solution is a vacuum solution.
No,
there ain't no mass or energy anywhere in that solution. It characterizes, something about the geometry.
Right? Yes, that's right. But if you, for example, so if you take like a star, not a black hole, like a physical star.
Yeah.
And you want to ask what is the space-time geometry and the vacuum exterior to the star. This is not internal to the star, exterior to the star. The Schwarzschild geometry has a parameter in it, right? Mm-hmm. In the it's 2gm over RC. Mm-hmm. That capital M plays a role in the theory. If you tune it to 0, then the geometry reduces to the Minkowski geometry. Mm-hmm. So here's just like a question you can ask, right? If there is some notion of gravitational sources and there's a notion of inertial mass, how are they related on general relativity? And the first person who appears to have, at least as best I can tell from the historical record, precisified this question was Steven Weinberg. And he did it in 1964, which was an incredible year for physics. I mean, Tim, 1964 is Bell's theorem. It's well, I mean, this argument I'm going to give in a moment from Weinberg. It's Penzias and Wilson's discovery of the cosmic microwave background radiation. Murray Gell-Mann and George Weig proposed the quark model in 1964. Jim Cronin and Val Fitch discover CP violation and therefore time reversal violation in 1964, right? And the Higgs mechanism is proposed by multiple people, right? Higgs and all in 1964. I mean, what are we doing?
Yeah, right.
What are we doing?
We're stuck. We are really stuck when you compare that to what's been going on recently.
Right. But so Weinberg is studying the relationship between quantum field theory, which is still relatively young in the 1960s, and gauge theories and general relativity. He's trying to understand the relationships between them. And he's trying to arrive at something like he's not intending to arrive at it, but it comes out of the calculation. He's trying to understand the relationship between gauge invariance and soft gravity. This is a whole complicated story that he was working on. But he ultimately arrives at this interesting statement that the gravitational charge, the thing that sources and feels gravity at the level of individual gravitons bouncing around in these diagrams, is not little m alone. It's this particular combination. It's written in the 1964 paper. The formula, I'm going to say it, but okay, it's not that complicated. It's twice the energy over c squared. Yeah, you might have thought it was just energy over c squared because E equals mc squared. M is it's not. It's twice the energy over c squared minus m squared c squared over E, the energy. It's these two terms. It's a difference of 2E over c squared minus m squared c squared over E, and it looks. What a funny looking formula. If you actually simplify it out for a particle that has non-zero mass, what you find is that it's equal to this relativistic Lorentz dilation factor gamma times mc squared like you would have expected, but there's a corrective, there's an additive corrective piece. Huh. It's actually that contribution times 1 plus v squared over c squared. And for very, very low velocities, the v squared over c squared goes away and the gamma goes to 1 and you get the usual Newtonian mass. But for a massless, or even a particle that's ultra-relativistic, and there should be a continuity between a very light mass, ultra-relativistic particle and a particle that's literally exactly massless level of general relativity. If you take the ultra-relativistic limit, the energy is so dominant it wipes out the second term and you get 2E over c squared, which means that the gravitational mass is twice what you would have thought the inertial mass was. It's an extra factor of 2. And so the gravitational force is twice as strong on that ultra-relativist particle as you would have expected, exactly the factor of 2 you'd need for that correction. And although Weinberg did this with this quantum field theory calculation, you can do it yourself. If you go to the Einstein field equation and trace reverse it, and then plug in for the stress energy tensor for a point-like particle. It's a delta function stress energy tensor. You'll just get this answer. It pops out. It's very beautiful. And it's closely connected. The M that it shows up in the Schwarzschild solution is closely connected. It's called the Komar mass. Anyway, so I just wanted to mention it's a beautiful story, and a little bit of a tangent, but one that I think isn't told often enough. So now let me get to your points. So you're completely correct. The wave function does other things. It seems to be connected with a clearly observable phenomenon, this interference phenomenon. So I'm going to tell you another thing that happened. So I was playing around with these non-Markovian stochastic processes that I had just sort of stumbled into. And I noticed something a little funny about them. So they had a very simple translation into a Hilbert space picture. And although I'm not going to be able to show the details and figures, Robinson, if you want, I can send a link to a talk I gave, a more technical talk, where I show one way that one sort of naturally arrives at this. But there's a way to construct a very elegant Hilbert space picture that describes this process. And then something really curious happens. Whatever initial probabilities you might have been using, the initial epistemic uncertainty, the initial probability distribution for the initial configuration of the system that then you're evolving forward with the stochastic process, that gets represented as a square positive semi-definite matrix in this formalism. This is the density matrix. And as you evolve it forward with this sort of non-Markovian process, this matrix goes from being diagonal to having off-diagonal entries. These are the so-called, in quantum mechanics, we call them coherences. And usually we talk about coherences in quantum mechanics. They're just primitive things. There's no interpretation directly for what the weird off-diagonal entries of this funny-looking matrix are. But if you take one of these processes and you impose an event, a Markov event, a moment in time when it becomes Markov and forgets its past, the entries in the off-diagonal, these weird off-diagonal coherences, they vanish. And this suggests a reducible meaning for them, that what they're describing is a kind of history or non-Markovianity in the process. And once you see this happen, it makes you a little bit, you're like, oh, wait a second. Usually we say that there's no meaning for these things, at least on this kind of a model. These weird off-diagonal entries, these coherences, seem to have some other meaning that we can give them. This is all very suggestive, to be clear. We're not yet talking about interference. But now what I'd like to do is actually give the simplest explicit model I can that would motivate this indivisible stochastic picture.
But before you do that, let me just try and get a little clearer about what you just said. And
yes,
and I'm hearing this for the first time.
Yes, I know. It's all very new.
Right. So we're all in the same boat. I mean, what I think I heard you say was that you have this stochastic process, fine. And instead of a precise initial state, you used a probability measure which represented some epistemic uncertainty about the initial
Sure, but that you could set it to 1. It's not necessary. Yeah.
Okay, if that's true, then I would expect all kinds of things to go away because that's just conditioning. That's just standard Bayesian conditioning, right? I make a measurement and all this a bunch of epistemic certainty goes away instantly because I found out among all these possibilities, at least cut down on them. So when you say all of these terms, if I have this later event, all these terms disappear. This sounds like what I would have expected if they were arising from an epistemic source.
I can make this more precise after I give a little bit of an example. So now I'm going to give this example I've been referring to, very simple example that will illustrate some of these ideas. And also kind of, in a sense, how cheap Hilbert space pictures and quantum-looking descriptions can be in some situations. So imagine the simplest dynamical process that we would call a dynamical process. Deterministic, time is discrete, it only happens in time steps. Let's say it happens every microsecond, something changes. And this system has a finite number of distinguishable configurations, let's say 17, because we used 17 earlier, let's say 17, a nice big, clearly not special number. Everyone knows the smallest uninteresting number is 26, by the way, but okay. So 17. So we've got some system. You could think of it in many ways. Maybe it's a strange, I guess 17 is not the number of sides in the Platonic solid, but maybe someone has some weird non-Platonic solid die that has 17, whatever you want to model. And I guess a die is a bad example because that would look too probabilistic. This is something that is just changing in a deterministic way. It starts in some configuration, let's say 3, and then it goes to 7, and then it goes to 4, and then it goes to 13, then it goes to 1.
Cellular automaton is what you've got, sort of.
Yeah, yeah. It's a very, very simple cellular automaton. That's one way to think about it. Every cellular automaton is a dynamical system of this kind. Just the cellular automaton, usually we think of it as like a linear array or a two-dimensional array or more of cells. I want to keep it even. I don't want to use any of that language. It's super simple. Okay, so the system is just going through these things, and let's assume the dynamics is so simple. It's logically reversible, which just means that from whatever configuration the system is in, the law will tell us what it will be in next, and will also tell us what it will be in before. So we get a nice one-to-one mapping, and we can predict exactly what the system is going to do. For this kind of a system, its behavior will end up having to be cyclic. Either it hits all 17 configurations and resets, or it doesn't hit all of them. If it doesn't hit all of them, just throw out the extra ones. But just assume it hits all of them. Okay? So it goes through some cycle, and then it returns to where it started. Couldn't be a simpler process. And every step happens at one microsecond. So here's the thing we can do with this process. And this goes back to a question I had a very, very long time ago. Because, when you're learning computer programming or learning elementary physics, you think about discrete time deterministic processes, and you wonder, can we interpolate them? Is there some smooth way to interpolate this to continuous time? Wouldn't that be interesting if there was some very natural way to do it? It turns out there's a very natural way to do it. As best I can tell, I think I'm the first person to write this down, although I'm not sure. I don't want to claim priority because it's very hard to search in the literature for whether an abstract idea has been done if it doesn't have a name. So probably it's been done before. But here's the thing you can notice. We can represent each of the 17 configurations of the system with a vector from what you'd call the standard basis. So imagine you've just got you people are probably familiar with 3D space. You've got the 3 basis vectors, I hat, J hat, K hat, right? It's a 17-dimensional space now. 17 orthogonal perpendicular directions. Each of them has a basis vector pointing in that direction. They're all perpendicular to each other. Now, it goes without saying that this is not a real vector space. It's not, it's physically real. It's a mental construct that we're just going to use. And now we can think of the system's configuration changing as a transition from one vector to another, right? It goes from configuration 3 to 7. That means it transitions from the 3rd basis vector to the 7th basis vector. What's really nice about this representation is that we can write down the dynamical law as matrix multiplication. We can introduce a matrix. It's a 17 by 17 matrix. It's called a permutation matrix. You can check that it's just made of zeros, except it's got a bunch of ones, and every row and every column is exactly 1 in it. And if you look at this matrix and look at all where the ones are, you can figure out what the rules are going to be for the system. The locations of the ones in this matrix tell you exactly what the dynamical law is. And then, of course, each of our basis vectors will be written as a column matrix with zeros, but then a single 1 in whatever. So the first basis vector's got a 1 in the first entry, the second's got a 1 in the second entry, the third in the third entry. Otherwise, all the entries are 0. And then we can model this dynamical process mathematically as just repeated multiplication by this permutation matrix. You just multiply it again and again and again. If you want to do 1 step, you multiply once. If you want to do 2 steps, multiply twice. And in general, if you want to do n steps, which is n microseconds, we're assuming that each time step is 1 microsecond, you just multiply your starting basis vector by the nth power of this permutation matrix. Okay. And this is a very beautiful story, and there's some beautiful mathematics, and you can talk about the eigenvalues of this thing, the roots of unity. There's this whole very beautiful story. But now I want to do something a little bit different. This permutation matrix, as a permutation matrix, a matrix that's made of zeros and ones, where every column and every row has exactly 1, 1, otherwise all zeros, is, in particular, a unitary matrix. So the word unitary, there's no avoiding mathematics here. I'm sorry. The math will be necessary. A unitary matrix is a square matrix with the property that if you flip over the matrix along its main diagonal, it's top from whose point of view am I talking about? If you're looking at a matrix and you look at the upper left corner and you draw the diagonal down to the lower right corner, you just flip the matrix over. And if the matrix has any complex numbers in it, which this certainly does not, but if it did, you'd have to complex conjugate also. And if when you do the double step of flipping it or transposing it and complex conjugate it, if what you get is the multiplicative inverse of the matrix you started with, we call the matrix unitary. Unitary matrices play a very central role. Earlier, when I was talking about the Dirac-Feynman axioms, I said that the evolution when a system is not being measured is unitary. That is to mean that it's described by a time-indexed family of unitary operators or unitary matrices of exactly this kind. And of course, this is not an accident. Notice we have a time evolution being carried out by a unitary matrix here, although in discrete time steps. And this permutation matrix is a very trivially unitary matrix. It satisfies the right conditions, but not in any fairly simple way. But here's the amazing thing about unitary matrices. We can take them to any power we want. And the result is still a unitary matrix. So I did talk about taking this permutation matrix and squaring it or cubing it or taking it to the nth power. Integer powers, these correspond to integer steps, but I could also set it to some fractional power. I could set it to some power that's between 2 and 3 or between 7 and 8. In fact, I can set it to any smooth real number power between those integers. And when I do that, the result is still unitary. It's not still a permutation matrix, though. In general, it will have complex numbers in it. Maybe people in who are listening know that when you take square roots of things, you can get imaginary numbers sometimes, complex numbers, things like that. Famously, the most elementary imaginary unit, I, is the square root of -1 in a formal sense. So you get now, at any time, smoothly interpolated time, anytime you want between the integer microseconds, you have a unitary matrix. And if I evolve, if I multiply my original basis vector by this unitary matrix at one of these intermediate interpolated times, I will in general not get a basis vector. I will get a linear combination or a blend or a superposition of the basis vectors with, in general, complex valued entries. And at this point, your thought might just be, well, that's curious. Whatever. Put that aside for a moment. We could do something else with this unitary but no longer necessarily real matrix, the 17 by 17 matrix, the permutation matrix, but set to a power that's some not integer power, some unitary matrix that complex numbers inside of it. We can do something else to it. We can define a new 17 by 17 matrix by modulus squaring every individual entry of the unitary matrix, one at a time. You modulus square the upper left corner entry and stick that in a new matrix. You mod square the next entry, you put that in the next entry of matrix. You can define entry by entry, entry-wise, a new matrix whose entries are all mod squares of the individual entries of the first matrix. The matrix we get when we're done has a very interesting history. It was matrices of that kind were first characterized in the math literature, pure math literature, real analysis, by Alfred Horn in 1954. He called matrices like this a matrix whose entries are all non-negative real numbers, but whose entries are entry by entry, the modulus squares of a unitary. He called those matrices orthostochastic. In 1989, they were renamed by Thomson in a lecture that I can't find. By the way, if anyone is listening and can find the text of this lecture, I've been looking everywhere for it. In 1989, Thomson gave a lecture. Johns Hopkins. It was at Johns Hopkins, but I can't find the text of the lecture anywhere, in which he renamed these things unistochastic. And now orthostochastic is used to refer to the case in which we don't start with a complex unitary, we start with a real unitary or orthogonal matrix. So orthostochastic matrices are a special case where the matrix we mod squared, we didn't even, it was already real. But if we start with a complex matrix, then we call the matrix we end up with, this 17 by 17 matrix with non-negative entries we've constructed, it's called unistochastic. And you can show that the matrix we get is a stochastic matrix. I said unistochastic, and the reason for that is a portmanteau of unitary and stochastic. By the way, portmanteau is a portmanteau. Isn't that funny? From to carry and mantle, it's okay. It's funny. But we can write that in a You can check that this matrix is in fact a stochastic matrix. Now, to be a stochastic matrix, that means that you have a matrix whose entries are all non-negative real numbers. And at least in this convention, we're going to look at the columns. Each column sums to 1. In the stochastic process literature, sometimes people work with what are called row stochastic matrices, where the rows sum to 1, and it just a matter of convention. But the one we get out of this is it's column stochastic, but actually it doesn't matter, because it turns out that for a unistochastic matrix, it's also row stochastic. It's called doubly stochastic or bistochastic, but in particular, the columns are stochastic. The columns sum to 1, I'm sorry. Okay. And what's fascinating about this is that a stochastic matrix defines a stochastic process. What I was doing before, where I took my basis vector and multiplied by this weird unitary I'd found at intermediate times, I could instead have multiplied my starting basis vector with this unistochastic, this real non-negative stochastic matrix I just constructed that just magically comes out. And if I do that, it also interpolates between the microseconds. But it doesn't interpolate with complex numbers or mysterious complex superpositions. It interpolates it with just a probability distribution at each intermediate time. So the picture that emerges from this interpolation of my discrete time process, it was discrete, it was deterministic, is I've now interpolated it to continuous time, where between the discrete time steps, we have a smoothly evolving probability distribution. And at each discrete time step, the non-trivial probabilities, well, it starts off with no probability, the probabilities are all trivial, and then as we go between the time steps, we develop these non-trivial probabilities, this non-trivial probability distribution, and then when we get to the next time step, the probabilities all snap back into being deterministic, and we just have a 1 and then zeros again. And so we have this very funny evolution where between the discrete time steps, we have an interpolation by a stochastic process with non-trivial probabilities. And at every single discrete number of integer numbers of microseconds, the system returns to being in a definite configuration. And you might ask, what kind of stochastic process is this? Is it a Markov process? The answer is it's not. It's not a Markov process. It's a lot like the kind of process that Shoemaker's universe had. It's a process where we can't divide up the evolution. The evolution just fails to divide between the integer time steps. So we have this evolution that is sort of indivisible between the time steps, and then it divides at each time step. It is an indivisible stochastic process. It's the simplest way to see these things emerge. I didn't give them, I did name them indivisible, but it turned out that the name had been given to them by Simon Mills and Kevin Modi in 2020, a couple of years before I arrived at them. So some interesting things to say about this. One is we get this very beautiful interpolation of our original process. We can now talk probabilistically about what's going on between the steps. We see that at these division steps, every integer number of nanoseconds, the weird complex superpositions that we would have seen if we were evolving forward with unitary, they disappear. They disappear at these special moments. What's also really interesting is, and now this is to come back to the complex version, I could again have evolved it forward with the complex unitary matrix, and then I would have had to introduce a Born rule to modulus square the entries of the state vector to get the probabilities. That's the other way you could have described the evolution. If I describe it that way, using this complex unitary where I have to do this mod squaring at every step to get the probabilities, if I do it that way, then the evolution is formally Markov. The unitary neatly divides. You just can multiply by any duration of time you want. If you give me the complex vector at any intervening moment, continuous intervening moment, you give that to me, I can evolve from there with I don't have to do anything about the past, using this complex unitary. By introducing this alternative unitary complex description with these exotic features, superposition and so forth, we get what looks like a quasi-Markovian description. And we get more. I mean, there is, after all, a unitary matrix smoothly interpolating time that's carrying this vector forward in time. And you can write down its generator. You'll find it's generated by a self-adjoint matrix, the Hamiltonian. That matrix has eigenvalues, energy eigenvalues. And so we actually get many of the features we would have expected to have seen in a quantum system. A Schrodinger equation. The system has a differential Schrodinger equation now. But none of these ingredients have to be interpreted as physical ontology. It emerged out of what is the simplest discrete deterministic model with the most straightforward interpolation. We can either view that interpolated model as an indivisible stochastic process in which the process is not Markovian, but there's also no exotica. There's no complex numbers. There's no wave function. There's no superposition. There's no Schrodinger equation, none of that stuff. And we'll get all the right predictions. Or we can introduce this alternative Hilbert space picture, which is mathematically equivalent. There's a correspondence. This is the stochastic quantum correspondence. And in this Hilbert space picture, we have a much more convenient evolution law where we can evolve from any time to any other time. The unitary matrix that carries out the evolution is way easier to use. We have a Schrodinger equation. We have eigenvalues. We have all this lovely stuff. And it's on this model that if you began with a non-trivial epistemic probability distribution for your initial state, then rather than a vector evolving, you would use a density matrix. And the density matrix ends up being diagonal at these special division moments, and then it becomes not diagonal. It develops these weird coherences in between them. If you understand how this simple model works, and I'm describing it waving my hands around, it is much less work to just write down. But if you understand how this works, it's very suggestive. It gives a strong hint about what could be going on in quantum mechanics. This is a model. I mean, it's a discrete model, but if you increase the dimension from 17 to a Googleplex, or I don't know, Ackermann's number, or some huge number, you begin to think, well, could you model any quantum system this way, really, to any level of precision? Now, what I haven't said, I haven't talked about interference yet. I haven't talked about the measurement process or non-commutative observables. This model has beables. The ways that it can be, those are labeled by the 17 possible configurations. But in quantum mechanics, we have theories like the Bohm theory, other kinds of observables we can measure. These are emergent interactions from the process of a measuring device interacting with a system. I call them emergibles because otherwise you have to call them non-beable observables, and I think there should just be a name for them. And so what we can talk about in a moment, if you'd like, is how all those other observables can show up, how the measurement process shows up, how interference shows up. But before I go any further, I've been talking for a while, so I'm going to stop. But I just wanted to stop now that I've written out that model and given you a sense of why you might be compelled to think that this could be so interesting.
Okay, so can I respond for a little while?
Yes, please. I'm sorry. Yes.
So this was, again, this is the first time I've heard this. I followed a bunch of it, I think. So let me explain in a different way what you at least described at the beginning. And why a bunch of stuff that you said didn't surprise me. I saw it coming, and I'm not quite sure how we've advanced the situation. So let me just, you started with 17, but for simplicity's sake, let's take a 3-state system, right? A nice little cellular automaton. It only has 3 possible states. And time is discrete, and at every time moment, it moves from one state to another in a deterministic way. It's going to go in a loop.
Just a small terminological thing. State is fine. I usually prefer configuration just because the word state can sound like quantum state, and I just want to be a little bit.
That's fine.
But you can say state. I just for people who are listening. Yeah.
I mean, if you're thinking in terms of automatons and machines,
yeah, we do call them states. That's fine. Yeah.
You know, yeah. If you think if you know Turing machines and stuff, you can just think of these as machine states, and the program is telling you that A goes to B and B goes to C and C goes back to A. This thing was supposed to be deterministic in both directions, so it's got to go in a loop. It's going to be a 3-step loop, or you could have one that's stuck and the other 2 bouncing back and forth, but let's do a loop. Okay, good. And now I specify the entire dynamics just in terms of that state transition which you could do in a matrix, the very matrix you described, bunch of ones and zeros that say this state goes to that state, this state goes to that state. All of that, I can use a matrix for. It'll be a very special, quite simple matrix. And I can visualize this in an abstract three-dimensional space, which is what you did, and say, well, let me take a space and let I've got three orthogonal vectors. Let this one represent state A, this one B, this one C. The dynamics tells me, this one goes to this one goes to this one, this one goes to this one. Okay, so I could do it that way. That's for discrete time, right? At each time step, again, it's very much like a Turing machine. At every time step, it does a straight transition. Now you say, well, gee, what if I wanted a kind of intermediate states? Well, I've got these vectors. I could say, well, let's just let this vector kind of smoothly at an even pace rotate from here to here. This one rotate from here to here. This one rotate from here to here over a microsecond. Now I have a continuous time evolution. It's going to give me the same thing at all the, microsecond things. But now I could say, gee, at half a microsecond, this guy's halfway here, and this guy's halfway here, and this guy's halfway here. Those don't really represent actual possible machine states, right? They're kind of superpositions, you could say. Right. Okay.
Formal superpositions at that level, yes. Right.
That's going to be, now you then have another thing that happens, which is you say, well, this is on the assumption that actually at every microsecond, it's in exactly one of these three states. What if I'm unsure? What if I think there's a 50% chance it's here and a 25% chance? Now I can stick a vector. I'm now mixing epistemic with other kinds of probabilities. And you have to be very careful about the term probability here. Yes. And that epistemic thing will be driven by this underlying dynamics, and it'll move around, right? And I guess I can imagine, although I couldn't see this right off the top of my head, that if I look at how these kind of states that are not in the definite directions go, it might not be Markov. That might not be Markov. I'm not sure.
Right. Yeah. In general, it's not Markov. That's right.
Yeah. So that might not be Markov.
Correct.
Right.
Yep.
That's okay.
Yep.
So I got all that.
Yep.
I think.
Yeah, that's
the worry was interference effects.
We didn't get there
because there ain't going to be no interference.
I didn't get to interference yet.
That's why I'm puzzled. I mean, there was a lot of math that went into that, and I think I was following most of it, and I seemed like it's kind of I mean, I think what I just described can give people a picture in their heads.
Sure.
We now have this vector moving around in a continuous three-dimensional space, whereas what's really going on is only a 3-point physical space, right? A 3-point state space, and you're just, moving at times between them. And then I'm putting all this other stuff in. Yeah, I can see how you can do that. And I can see it would have a lot of the properties you gave, but I'm not quite seeing where I'm getting out of that.
Okay. So I'm so glad you have a picture. I didn't pick 3, by the way, just because I didn't want to confuse anybody watching that this is like physical 3D space.
Yeah. I picked 3. I can only do it.
I know. That's the thing. Exactly. Right. If you have tesseract hands,
or
you should get that checked out.
Or whatever. Sure, yeah.
Right. Okay. So no, your picture's right. On the one hand, so let me just quickly address your question about probability here. The simplest way to talk about the probabilities that are so there's 2 ways to think about the interpolation, and you illustrated both of them. One way to think of the interpolation is a probabilistic interpolation, where the vectors are kind of, if you want to visualize them in this abstract space, they're kind of rotating into each other, but not really a rotation. They're also deforming or stretching a little bit because the coefficients have to add up, to make 1. They're probabilities. They're all non-negative. Yeah. That's one way to think about it at the level of what the individual vectors are doing. And this is when you write it down in mathematical terms, it's exactly the form of one of these indivisible stochastic processes that have been characterized in literature. They're not Markov. Or we could think of them as really rotating, but then the coefficients aren't going to add up to 1. You have to square them, and then they'll add up to 1. And that alternative interpolation is Markov. It's like rotation. You can divide it up. It's nice and Markovian looking. That's a lovely way to think about it. In general, when you do this, though, the entries will fail to be real valued. They'll entail complex numbers. So it's not just rotating in ordinary 3D space with ordinary numbers. You'll need complex numbers as well. But of course, what you can do if you take this complex now vector sticking in some intermediate direction and you mod square its entries, you get the vector from the first version. And so the flat-footed way of saying is, okay, what's going on here is I have interpolated my discrete process at the my deterministic process at discrete times to a stochastic probabilistic process interpolating between those discrete times. And I can represent it either with a unistochastic matrix, then it looks like an indivisible process, or I can use complex numbers just as a useful mathematical tool. And then I get all this other beautiful, wonderful stuff. But I also have a lot of exotic new features like complex numbers and Schrodinger equation and unitaries and all that stuff. So your picture sounds like you get it completely. This is great.
Okay, can I just make another?
Yes,
I
please.
actually was going to say this at the very beginning, and
Sure.
I forgot to say it. But just so people understand, when we're talking about the mathematics, there's a thing called a probability measure. That's just its name. It's a measure. It has to be normalized to unity.
To be clear,
The
measure is not measurement. To make it's a mathematic. Yeah. Okay.
If I have a space, if I have two pieces that don't overlap, the measure of their union has to be the sum of their measures. Okay, so there's some formal features that a measure has to be called a probability measure. But the word probability could really mislead you there. You know, if you're just talking about plain old statistics, they have to be described by a probability measure. They have to add up to 1, right? Percentages have to add up to 1. They can't be negative. You know, the percentage that are in the union of these two groups has to be the sum of the percentage in each group. So you use them to describe statistics. You also use it to describe a stochastic process, meaning a non-deterministic process. This is a dynamical notion.
Yes. Yes.
You also use them, many people use them to describe people's beliefs. They use probability measures to measure credences. I myself think this is a bad idea, but pretty much everybody does it. Okay. And they're all mathematically probability measures. But the use of them doesn't mean that you're introducing stochasticity or denying determinism.
Agreed.
Right? So you really have to track, when you say that's a stochastic process, I mean, the process we started with was a deterministic process. And even with the interpolation, it really wouldn't normally be what I would think of as stochastic process, right? Where from a given state, there are definite probabilities of how it will evolve, right? It's just give me this state. Okay, it doesn't have to go this way, but there's a probability in the sense of a number between 0 and 1, or a probability density that it do this, that it do that, that it do that, right? And so even though we talk about and at the level of matrices, you won't see any difference because this is all the same math. It's all just probability measures. So one does need to track what the hypothesis is here, right? One you really want to track is, are we giving up transtemporal determinism or not? Can some complete initial state evolve differently, or is there only one way it can evolve? How constrained is it by the laws? So
I have to just say, this is one of the reasons why I'm enjoying talking with you so much, because your insistence on precision. So when I think about analytic philosophy, I'm not going to define just the definition of analytic philosophy, but one of the things I think is really characteristic of analytic philosophy, when I'm talking to scientists, to physicists, and trying to explain to them why it's worth their while to learn something about how to think a little bit like an analytic philosopher, is that eventually the experimental data and the mathematical symbols dry up. If you're a pure mathematician, that doesn't necessarily have to happen. But if you're doing science or physics, there's always going to come a moment when the mathematical symbols and the experimental data dry up. You can't just say, I don't need any, just go with the math and the experimental data, because at some point it stops. And we're seeing this exactly right here. I gave you a bunch of mathematical representations, and you did exactly what an analytic philosopher is great at doing, which is, okay, well, then what? When the symbols dry up, how do you get to the next step? And good analytic philosophy is learning how to understand what it means to try to be rigorous after the mathematical symbols and the experimental data dry up. It's one of the lessons I try to convey when I talk to physicists. I teach philosophy and physics classes, and when I teach my physics classes, I'm especially trying to get across to the physics students why it's so important not to think that you give up on rigor the moment this mathematical symbols dry up. So I'm really glad that you brought this up.
Well, can I just make a little comment about?
Oh, sure.
I mean, this is a really important case for quantum mechanics because a whole bunch of physicists were under the mistaken impression that when things decohere, which you can kind of define mathematically, you're entitled or allowed to suddenly take something that has nothing probabilistic about it, really probabilistic about it, and interpret it as if it's just epistemic uncertainty, right?
Yeah.
And elide the measurement problem in that step, which is completely illegitimate.
Yep.
It's a completely illegitimate
I
step.
completely agree with you, yeah.
Because this is just, I'm not saying it to you. I'm just saying
this
is more than just nitpicky stuff. I mean, people being unclear about what the probability measures are that they're throwing around mathematically has been the source of a tremendous amount of confusion about the problems with quantum theory, because they thought they could solve them by getting a certain number to look like another number and not seeing that, but to interpret it this way and then to interpret it that way, that's not automatic, even if the numbers look similar, right? That's, I just wanted to point that out.
What I was talking about, the two different kinds of evolution in the Dirac-Von-Neumann axioms, and I said that they're categorically different. One does not have, decoherence is on the Hilbert space side. And you can't just say, well, there's decoherence. The density matrix looks kind of like it would if we were imagining probabilities, and therefore they're probabilities. So everybody who's listening to this discussion should just stop right now, just pause, and go find Tim's paper, 3 Measurement Problems, which is one of the paradigmatic papers in quantum foundations. It's 1995. I think it's in Topoi, the journal, TOPOI. And you identify exactly this elision, this mistake, and you describe it as mistaking necessary versus sufficient conditions, right? So, right, and this is a thing that happens constantly in the scientific literature, is people confuse necessary versus sufficient. It is the case that if somehow the entries of your density matrix have become probabilities in the right sense, classical-ish probabilities, then it is certainly necessary that it should look diagonal or whatever, but it's not sufficient, right? And this confusion of necessary versus you identify it quite precisely, and it's when I try to explain to physics students an example of the necessary versus sufficient condition mistake, I often point to that exact point that you make in that paper. So anyway, so getting back to probability, I want to make very clear here, I'm not talking about a physical process yet. I'm not saying that nature has some discrete process in it and I've derived probability. I am 100% not saying that. I'm only saying that if you're a student and you're like, I could model a thing like this, could there be, not this process, but could there be some probabilistic process that agrees with my deterministic process at the nanosecond, the integer nanoseconds, but is a probabilistic process and has probabilities in between? What kind of process would that look like? Is there some very simple construction, right? And although it took me a little while to explain it because I'm using words, I feel like a nominalist. I'm like trying to explain everything without using math. But if you like read it out, it's actually like a few steps. It's incredibly simple. It gives a very nice analytic interpolation. And if you wanted to regard the true process, if you wished, as a probabilistic process, you could. And then it would be kind of up to you how you wanted to make sense of the probabilities. You're completely correct. It's not enough to say I've got real numbers that are non-negative and add 1. When I talk to physics students or math students, and I ask them what's the probability, they'll say, oh, that's easy. It's defined, but I mean, it depends on how much math they've seen. But, they use the 1933, which is curiously after quantum mechanics was formalized, 1933 Kolmogorov measure theoretic definition of probability spaces. They're just like, oh, to have a probability means that you have a probability space. You've got a measurable space, and you've got a a distinguished collection of subsets. The sigma algebra, it satisfies various set theoretic requirements, and then there's this map on the on that sigma algebra to real numbers between 0 and 1, and it satisfies normalization and additivity and all these various things. And that's the rigorous definition. And I say that's not the rigorous definition. That's not the rigorous definition, because that applies to, if you take Earth and imagine slicing Earth up into chunks, and you just treat every chunk fractionally. How much of the Earth is this chunk? That will also satisfy the same axioms, and it does make it a probability, right? The math has run out, and now you need something after the math, right? You haven't given me a rigorous definition of what a probability is. So I 100% agree with you. 100%, sorry for the pun. You could think that the process you're starting with is describing just statistical behavior of many systems. You could think of it as describing an objectively chancy process. Another paper I recommend people read is, again, sorry, Tim, but your I think is your 2007 paper, what could be objective about probability. I think it's the paper. It's a lovely paper. You talk about the different ways we could think about chancy probability, or I guess you could think you're modeling a process where the probabilities are really standing in for something like credence, subjective credence. It's up to you. It doesn't really matter to me. For my purposes, I'd like to think of this in the objective chance sense, that the probabilities I'm using here, the stochastic process I'm describing, are talking about objectively chancy laws. But to be clear, I'm not taking a discrete process and then I'm starting the other way. I'm saying that that we could imagine there was some underlying process the whole time. Okay. But now let me move on to, I think are we good there, or should I move on? Can I move on to the next step?
I think, yeah.
I think everything seems like it's perfectly agreeable. Okay. So you can start to ask some questions now. I mean, I have this probabilistic process. It could have as many configurations as I want. You pick 3, I pick 17. It could be a Googleplex, Plex, whatever. I could make the intervals between these Markov moments longer than a nanosecond. I could imagine a process where they're separated by 1 million years. I mean, whatever. And now I can ask some questions. What if my configuration, each configuration, so that there's a 3 configurations, 17 configurations, a Googleplex configurations. Take a set of all of them. We call that a configuration set or configuration space. It's just the menu of the possible arrangements. And then let's imagine that what we're describing really is a mereologically composite system of some kind. So we're going to think of each configuration as an ordered n-tuple. Fancy language, just an ordered list, okay, of the configuration of 127 systems, something like that, okay? So every configuration is really telling you a list of all the configurations of 127 different constituent systems. And we can get into a discussion, are these elementary? For our purposes, they're effectively elementary. Last time Robin and I talked, we talked about the fundamentality of nature. I'm not going to, we're just modeling. We could assume these are the mereological atoms of nature. We could assume they're coarse-grained. This is immaterial for the present purposes. Okay, so and if each of them has, some number of configurations, then the overall size of the configuration space is going to be some combinatorial, how many configurations the first system has times how many configurations the second has, and so forth. That will be the overall number of configurations of this whole system. Okay, and now what we can do is we can write down these. We had this stochastic matrix. It's made of these conditional probabilities, that we think of it as a stochastic process. The conditional probabilities will not be Markov. They won't be divisible. Slightly different notions. And now what we can do is we can start asking some questions about what happens when we marginalize them. So in classical probability, if you have the probability for some collection of objects, such and such is the probability that this collection of objects will have this overall arrangement. There is just an ordinary probability notion of ignoring all but one or a few of them. This ignoring is called marginalization. Formally, it's a sum, but I'm trying to avoid mathematical language, but it's just conventional probability stuff. And we can ask, okay, once I've done that, what happens? Do I get anything interesting? And what's really interesting is that with very, very simple models, in fact, I have one that I'm hoping will end up in a paper at some point. I just literally haven't had time. It was part of a lecture note that I gave. I can also send you a link to it. I do this for a very simple problem. Suppose that my system, forget all the complications, suppose I just have a two configuration system. This is ultimately going to model a qubit. Sorry about etymology, but do you know where the word qubit comes from?
I assumed it was from quantum bit, but
interestingly, that's only half the story. So I have this on good authority from one of the former students of Ben Schumacher at Kenyon College. Ben Schumacher and Bill Wooters work in quantum information, and they coined the term qubit 1991, 1992, because they didn't have a name for a two-element quantum system. Bit itself is a portmanteau of binary information digit. John Tukey introduced that in 1947 and then was popularized by Claude Shannon of information theory. And they were joking how Bill Wooters at Williams College and Ben Schumacher at Kenyon College, they were driving back to the airport in Ohio. Ben Schumacher, I think, was driving Bill Wooters back to the airport. And they were joking, wouldn't it be funny if we call these things qubits, because in the Bible, there's a unit of measure called a qubit.
Oh.
And it's written C-U-B-I-T, right? And it's supposed to be the distance from, your elbow to the tip of your index finger. And if you read the Bible, when I reread, the story of Noah, and I'm like, it says qubits in it. I'm like, qubits, what's going on here? And because C is for classical, you see, because what's more classical than the Bible, right? And so they just replaced the C with a Q. And David Mermin, who probably people who think about quantum foundations and read about it probably know, and he's a physicist who thinks a lot about quantum foundations, has always thought this was a monstrosity of lexicography or whatever. QU and then a consonant. That's not a thing we do in English. He insists on writing capital Q and then BIT with no U in it. But the whole joke was that it was supposed to be a play on the biblical qubit. That's why it's QUBIT. So just funny story. So imagine we're now going to do this story I just told you about. Just told you about the story. And suppose that we're going to consider a system with just two possible configurations is going to model our qubit. And we let this qubit evolve according to this indivisible rule. And in the simple version, and Tim will be the first to say that the details of the double slit experiment, like the full fine-grained details, are actually quite mysterious. And when people describe the two-slit experiment in quantum mechanics, they never give you the detailed full story. They always simplify it in some way. And I'm going to simplify it because it's sufficient for my purposes here. So imagine that we've coarse-grained our whole experiment so that we just have these two configurations. Think of them visually as upper part of chamber, lower part of chamber. Think of it as a super coarse-grained version of the double slit experiment. And this thing evolves from time 0. And then there's an intermediate time. This intermediate time we'll call T prime. And T prime, this intermediate time, is where the holes are, if you want. But really, we're just going to, the system is either upper or lower. It's definitely one or the other because this is just a classical stochastic. I mean, it's ontological classical. It's at any moment, it's always one or the other. And think of this as it's either in the upper hole or the lower hole at T prime. And then at some final time, TF, T final, we can ask about what the probabilities are. And the model I gave you lets you compute probabilities whenever you want. We find something really interesting with this model, super interesting. We find that if you tried to write down, remember I gave you this underlying stochastic quantum whatever, you might naively ask, I mean, not Tim, you asked this, but a person look at this would just say, well, wait a second. I have a unitary time evolution matrix that takes me from any one time to any other time. If I mod square its entries, I get a stochastic matrix. Why can't I just use the stochastic matrix I get from all the I can just take every intermediate unitary and just use the stochastic matrix from all of them and just multiply them together? Why can't I just do that? If you do that, you get the wrong answer. And you can see it very clearly in this example. If I naively compute the probabilities for the qubit or the two configuration system to be in either one hole or the other. I just compute those probabilities. And I pretend that from here, I can then evolve the system forward as if it were Markov, ignoring the past. Then I will get the quote-unquote classically expected probability distribution at the end. But if I say, that's illegitimate, the process is indivisible, I'm not allowed to just slice up my stochastic matrix at intermediate times, that wouldn't properly reflect what's really going on in the process. If I evolve the system correctly, not assuming there's a Markov event in the middle, I get a different distribution of probabilities at the end. And if you subtract from the correct final distribution, from the truly indivisible process, you subtract the Markov approximation where we pretended we could just, if you subtract the two, then the discrepancy is mathematically exactly the same as the formula for the interference effects. Like literally exactly the same formula. And when you look at descriptions of the double slit experiment, for example, the beginning of Feynman Volume 3, where he introduces quantum mechanics to double slit experiment, I don't remember if he says this explicitly or it's implicit in the discussion, but at some point he says, well, look, the thing either goes through one hole or the other. Suppose it goes to the first hole, then what would the distribution look like? Okay, now suppose it goes to the second hole, then what would the distribution look like? And now we just average over the two. But that's explicitly making a Markov assumption. If you simply don't make the Markov assumption, and you don't have to do any work here. It's not like you have to write down some very complicated, bespoke thing. If you just take the simple model I gave you that super simple model, and you just let the evolution be just that unitary that we got without any real effort, you'll get the wavy interference effects without having to sit and say there's a wave there. Now, the first time I saw this happen, it was very surprising to me because, like everybody, I'm like, well, I mean, if it sounds like hoofbeats, think horses. Of course, every time you do the experiment, you don't see the waves. So this is important to make note about the double slit experiment. You do the experiment, one particle lands. You do the experiment, one particle lands, and over 10,000 run of the experiment, you get a distribution of dots that show certain bands where they tend to like to land and other bands where they don't. And from this, we infer that something wave-like has been going on. And like many people, I assumed, okay, that must mean that there's just something wave-like in this picture. It gets complicated if you're trying to send 2 or 3 particles into the experiment at once, then it gets very complicated because with 3 particles, the wave function lives in a 9-dimensional space and whatever the holes are. But the point is, when I first saw that a process that was just this simple, discrete, I just started with this process and extended it, interpolated it in this way, and I got discrepancies between the true evolution and its sort of most obvious Markov approximation. And those discrepancies were exactly the formula for interference. That was very surprising to me. And that had a big impression on me. I'll stop there for a moment because I know there's more to say, but I'm going to stop there for a second. Yeah.
So we're running out of time.
We are, yeah.
And a lot of that went real quick, and I'm puzzled by a couple things, and I'll just say what I'm puzzled by.
Sure, please. Yes.
So, I mean, one is you say it's a 2-state system, but by the time you get to the screen, there better be a whole bunch of states that is their locations that they can land, right? Or else I don't see what I'm going to see in terms of interference bands. So I'm a little puzzled. Let me make another comment. Feynman's argument in his lectures is dreadful. It's just wrong. It's just wrong. He thinks from looking at statistics with one slit closed and the other open, and then looking at statistics from the other slit closed and this one open. And that in just probability theory will give you a prediction for both slits open. That's crazy. Probability theory won't tell you anything. As far as probability theory goes, the whole thing could blow up when you open both slits. Anything could happen. Right. Probability theory doesn't tell you what will happen. Right. He's making an assumption that if it goes through one slit, that the openness or closedness of the other slit can't make any difference. It must be irrelevant. That's false. And that's what we know from this experiment for sure is false. We put a phase shifter in one of the slits and we'll get different interference bands all the time. So, I mean, that argument that he gives there where he's suggesting, gosh, we have to go beyond classical probability, that's crazy. He was way off base. right?
You're preaching to the choir, Tim. Totally agree.
So,
I'm upset that we begin. A lot of students first see quantum mechanics starting from this argument. I think it has a lot of problems. Okay, so you're 100%. I'm doing it with a two for simplicity, two configuration. You can do it with 1,000. In fact, I was contacted by someone who was very interested in this theory, and he decided to do it for a system with way more ingredients, and you begin to see what looks like the standard interference pattern show up. But I want to make now the extra thing, because now we're seeing what looks like interference effects. And by the way, this is also reducing what interference is. This is now saying interference is a very different thing from what we've been saying it was. It's not a question of waves. Interference is just a discrepancy between evolution that's truly not Markovian and whatever convenient Markov approximation you might have wanted to make. I mean, Markov approximations are extremely useful. We model stochastic systems in nature all over the place that we have no good reason to think at the level of coarse graining we're working at should be treated as Markovs. People use Markov stochastic processes, Markov chains, to model lots of phenomena that we know are only approximately true. And then there's a discrepancy because our Markov model is not going to get everything right. My claim is that those discrepancies, broadly speaking, are what interference is. And the interference of quantum mechanics is just one more example of that discrepancy between Markov and non-Markov. So this is all very suggestive, right? I mean, I'm not just proposing this. It just pops out and it's very exciting and very suggestive. But it gets even better. Now let's suppose that we make the experiment a little more complicated. Let's suppose that we introduce an extra qubit that will serve as a detector, okay? And this is not going to be an external abstract primitive observer. I'm going to model the whole thing as one big stochastic process. So now I've got 4 configurations because I've got the 2 for my first qubit, the actual traveling one, and then 2 from the detector qubit, and just it's 4 possibilities altogether. And I'm not going to be able to go through the mathematical details in the time we have, but again, I'm happy to direct people to the description. But if you give the detector a very deterministic kind of dynamics, which we're modeling it how we want to model it, if we model this detector so that if our traveling qubit is in the upper region, then the deterministic detector stays in its original initial configuration, doesn't change. If the traveling qubit goes through the lower part of the apparatus, the lower hole, I guess, then the detector qubit transitions deterministically. It definitely transitions, okay? And this is obviously an idealization, and you can drop the idealization, but I'm going to idealize it just for present purposes. So the little detector is very deterministic in how it behaves. You can model the whole thing as one giant stochastic process. The matrix gets big because it's now going to be a 4x4 matrix, and you have to write everything out. It's not convenient, but the point here is not convenience. When you marginalize over the detector, classical marginalize, no quantum tracing, whatever. You just want to know, okay, what is the final probability distribution for the original traveling qubit going to be? The interference effects go away. They disappear. They exactly disappear. And if the interaction between the detector qubit and the traveling qubit is not perfect, it's not ideal, then you won't completely lose the interference effects. You'll only lose them partially. Now, why would we marginalize? Because realistically, a detector is going to be part of a much bigger macroscopic thing. We can't possibly keep track of everything. We marginalize the same way we marginalize in any classical ordinary probability story. And we lose the interference effects. And at the level of the stochastic law, we get what looks like a Markov event. The indivisible unistochastic matrix factorizes across the 2 times. And suddenly we get the spontaneous generation of a new division event that wasn't there before. It's not a global statement. We're not saying the whole universe as a division event. But at a mereological levels, for the mereological level of the original traveling qubit, it has this division event. And although we don't have time right now because we're just out of time, I've axiomatized this indivisible theory. And so you have to be very precise in the axioms how you deal with these spontaneously generated division events. But there's no assumption here that, and I know this is obviously a very delicate question, Tim, but I don't want, I'm not going to make a metaphysical statement about this. This is just a math statement. But at a math statement, there's no time irreversibility or violation of time translation invariance at a global level, except maybe the very first initial to get the process started. But what you get is you get spontaneous breaking of time translation invariance and time reversal invariance because these interactions are directed. The qubit, the detector qubit evolves differently forward from how it evolves backward. And this means that the evolution is Markov to the past, but not to the future. And so there's a sense in which, you're getting forward evolution that's definitively forward evolution from that moment. And so you're spontaneously generating this sort of arrow of time. I should just hasten to add, and this is just a nice, funny additional feature, is that unistochastic matrices, because they're doubly stochastic, have another very interesting property. They are entropy increasing. A doubly stochastic transition matrix always increases, or at least the entropy is always non-decreasing. So it maps on rather beautifully to, obviously more work is here to be done, but beautifully to a kind of sense in which we're getting something like the second law. So that's a lot. I apologize. There's a lot to say there, but my only point is that once we can do these sorts of experiments, you're like, oh, what other kinds of measuring apparatuses could I have? Could I modify the dynamics of my detector qubit? Just give it a different change the stochastic dynamics so that it could measure other things that are not beables, not the up or down configuration. The answer is yes, it can measure other things also. The things it's measuring in this case are not transparently reflecting the ontology of my traveling qubit, but as far as the detector is concerned, the detector gets a reading on them. And as far as the detector is concerned, it looks like it's just measured something. And so this can account for the contextuality of observables in quantum mechanics. We've got the beables, which in Hilbert space language form a commutative subalgebra of the full algebra of observables. And we also have these other non-commuting observables, what I call the emergibles, which Bohr described in 1935 as being emergent results of the interaction of a detector and the system being studied. And you get those too by just changing the dynamics of the measuring device. These measuring devices in this indivisible theory can measure lots of things, some of which are measurements in the literal sense that they're revealing some existing property. And in other senses, they're measurements in quotation marks, the way that Bell said we shouldn't call them measurements because they're not revealing something. They're just an experiment that produces some result with some probability. And I hasten to add that you can compute the probabilities with which the detector will get results from any of these things, and they accord with the predictions of the Born rule. So this is obviously this was not, I didn't begin this project thinking that this was going to work, but every time I thought, oh, we're certainly not going to be able to have this show up or have that show up, stuff just shows up. So the picture of the world that I'm describing here is a picture in which there's just a configuration of the world, like the shoemaker world, and the laws are indivisible, they're not Markovian. But they can be represented in a quasi-Markovian sense using a Hilbert space picture. The regalia, the appurtenances of a Hilbert space picture collectively make it into like a hidden Markov model with complex numbers and lots of arbitrariness in the definition of things. And that's kind of the picture of the world that's here. It's a very simple to axiomatize. And in a sense, it's kind of modest in terms of what it's demanding of nature. I'm not saying that one can't propose that the additional ingredients of the Hilbert space picture, like wave functions or quantum states, I should say, can't be there. I'm not making an argument that one is obligated to avoid reifying those things. I'm just saying that from this point of view, one could think of it as optional. If one wants a somewhat more humble or modest ontology, in the sense of only having local beables and not introducing more stuff, you might think you have to make the laws unbelievably complicated. Tim earlier said if you remove the causal Markov condition, you get a proliferation of extremely complicated causal Markov models. You might have worried that would be the case. I was worried that would be the case if you drop the Markov condition. But it turns out that these indivisible processes are in some sense even simpler to formulate mathematically than Markov processes. They have fewer ingredients in them. When you actually write down the stochastic laws, you find that they're in some sense sparser and simpler than they are even for a Markov chain. And finally, you get back to the question of how we get the causal Markov condition back again. If you've got a big macroscopic system, it's undergoing these division events all the time. They are the stochastic process analog through the stochastic quantum correspondence to what on the Hilbert side we would call decoherence. And either decoherence is getting rid of interference effects from macroscopic systems, or it's not. And if it's not, then quantum mechanics as we know it is wrong. But if it is, then on the stochastic process side is describing the generation of all these Markov events. And so for macroscopic systems, we return to essentially a Markov process. A Markov process, the causal models you'll build out of these things, we don't have time to talk about causality, but the causal models would satisfy the causal Markov condition. And Ehrenfest's theorem will say that the averages, which are now bona fide averages of things happening, are going to evolve in a way that resembles classical equations of motion. So there's a lot more details to say that we didn't have time to talk about, but broadly speaking, that's the picture I'm actually presenting.
Okay. Well, I'm sure we've tried the patience of anybody who's still listening. Let me just say 2 words in response. Okay. For anybody else, a lot just happened.
Yes.
From the last time I read a word to now, you just made a lot of claims.
Yeah.
And we obviously don't have time to go through them. I have to say, I'm still puzzled, and I'll just state why. From the beginning, I said, gee, we've got these interference effects. This kind of interference we associate normally with waves, water waves, electromagnetic waves. I think there's probably something in the physical world that's a wave, that's a field-like thing that evolves by a wave equation. That would at least be an obvious way to account for that phenomenon. Now, you're telling me you can account for it without that by this. I can't absorb. There's just no conceivable way you could explain or I could absorb how any of that's supposed to work. And whereas in the beginning, when you were just talking about these, putting in these intermediate things I could follow, just for anybody at home, if you couldn't follow, I have to say I couldn't follow. There's a lot of stuff there that would probably take a long time to work through. But that's, I think, just where we need to,
that's entirely fair. I will refer you and anyone who's interested to the detailed calculations. There's a write-up on just the qubit case. There's a more recent paper that I can point you to where a more extensive calculation for more states was done. And then the general theory of how we get these division events to show up is in a paper that's published in the Journal of Philosophy of Physics just this calendar year. So some of those are technical. I mean, you have to do some work. It's not like this whole project is just trivial.
Sure.
Conceptually, like the axiomatic ingredients are simple. We just have configurations that are evolving indivisibly, and that's kind of the story. But to then show that this is empirically adequate and can save the phenomena, can account for the things we see, that's going to require work. And I'm not going to propose that we do quantum mechanics practically in this way. I mean, there's no question that hidden Markov models are very convenient. I mean, there's a whole theory of epsilon machines that is very, very interesting that people can look up. Crutchfield, and so forth, developed that to handle non-Markovian systems as hidden Markov models, and everybody loves using these. They're really very powerful. They're very abstract, and we make them a hidden Markov model by introducing like fake extra stuff. And I should just say that now that I've covered all of this, let me now quickly turn around and just say, when you have a stochastic process and you introduce an extra hidden or latent variable, and the language is a bit ironic because now the wave function or quantum state is the hidden variable, not the local beables. When you do that, in general, for a hidden Markov model, this new variable will have an extraordinarily large number of configurations. This is another telltale feature that you've got a hidden Markov model, which of course is also true of the wave function. But there are also some problems of uniqueness. And this is a question I wanted to ask you, Tim, because it's been bothering me a long time. So, and the answer might be simple. This is not a gotcha question. This is something I'm just very, very confused about. In the Bohm picture, there's a pilot wave. It's a wave function. It's a complexified function in configuration space, and this equation guides the particles around. There's a class of transformations called Foldy-Wauthausen transformations. I doubt most people have heard of them. They were introduced in 1950 in the context of the physics of spin half particles, the Dirac field. And they didn't really make their way into the philosophy literature until Harvey Brown, I think independently, re-derived them in a paper in 1999 called Aspects of Objectivity in Quantum Mechanics. It's on the first page. You can just see it right there in that paper. It's a class of transformations that change the quantum state or the wave function. Now, on the Bohm theory, the local beables are particle positions, and Bell himself, and I don't have to check exactly what Bohm exactly said, but Bell certainly said this, argued that all the empirical output of the Bohm theory supervened on the distribution of positions of particles. Now, that's fine. There's no, in principle, issue with that, except that these transformations you can do, there's a restricted class of them, the class that commutes with the position operator. And these transformations mangle up the wave function, but don't touch the mod square of the wave function, don't touch the positions at all. And they alter the guiding equation. They alter the trajectories. And there's no canonical frame to use in the sense that, like, there's no preferred, like, you can do one of these Foldy-Wauthausen, these restricted Foldy-Wauthausen transformations. What they effectively do is they change the phase factor of the Schrödinger wave function by a space-time dependent phase.
Mm-hmm.
And this doesn't change any of the mod squaring. It doesn't change the probabilities of the overall, I should say, the overall wave function. It's not, the whole thing. But it does modify the guiding equation, and it changes the trajectories the particle takes. But because, by assumption, or by argument, I mean, the question is how you rigorously show this, that all of the empirical output supervenes on just the positions of the particles or their distribution. This troubles me because it seems like the guiding equation and the trajectories of the Bohm theory are radically unfixed. And I'm wondering if you can maybe help me understand why I should not be worried about this problem.
I mean, I think I could. I'm sure Robinson wants to gnaw his foot off at this point about another thing. Let me try in 1 minute to say, look, everybody who works on the pilot wave theory knows you can actually change the guidance equation in certain ways that won't change the statistics for the outcomes. Okay, that's well known. Often those changes look just crazy and arbitrary, and you wouldn't do them because they just look kind of loopy. And we need to make a distinction between gauge transformations, active transformations, passive transformations. It's clear you can pick any mathematical object, screw around with it in some way, screw around with the dynamics in an opposite way, and end up with the same empirical predictions. So, the question is, if the wave function represents a real physical thing, what are its merely gauge degrees of freedom? What are its physical degrees of freedom? That's not an easy question. You can answer it like the overall phase. Does that correspond to a physical degree of freedom? Or is it just an artifact of the representation? I don't think there's an algorithm to answer that. I think you have to look very carefully at the individual cases. Often normal things like you're doing something really screwy there for no purpose will make one look a hell of a lot more plausible than the other, even if you say, gosh, but the appearances would be the same. But I think these would be very detailed questions you'd have to go through, and there's not a one size fit all even algorithm to try and sort through it.
Yeah. So the reason I just bring this up is these Foldy-Wauthausen transformations are very simple. They look just like electromagnetic gauge transformations.
I would think they sound like local gauge transformations of electromagnetism.
Yeah, except that the gauge connection is the Hamiltonian. It's this weird thing. But the argument, I mean, you can make the phase of the universal wave function on the Bohm picture. You can change its phase at every space-time point to any other phase you want, which makes it very hard to think that the phase at all, at any point, is somehow physical or not gauge.
A local gauge transformation. We're kind of familiar with that stuff. But anyway, I think this would take us
this take us a long time. Yeah. But this worries me. It's one of the things that has made me skeptical that the pilot wave could be physical, but it's not an open and shut case. To make clear, I'm not making any open and shut cases here.
Mm-hmm. Well, I wish that within the span of 3 hours, it were ever possible to really resolve a substantive issue in either philosophy or physics. But I'm really glad that we got to have this, or I got to host this conversation on my show, and I hope that it continues either on mine at some point or on another show. And I'm sure that there's plenty that a lot of people would love to hear the two of you talk about. But for now, thanks again so much for joining me for this.
It's a real delight. It's lovely to see you both. Be well.